Finite state machine. The state. As we know in formal language and automata, the basic concepts are finite state machine. That is, in short, we can say FSM. So at first we have to know what is FSM. So FSM is finite state machine. It is a mathematical model that can be in exactly one state at a time. It moves between states based on inputs. In FSM, each state there can be multiple states, and each states are connected by edges. So here, uh, so here we are giving. So we have. So here we are talking about the finite state machine. Here the number of states are limited. That is not infinite. That's why we can call it finite. Now comes the state, distinct situations or conditions. There can be transitions, and there are also rules for moving from one state to another. Simple analogy, as we can understand in the traffic signals colors goes from red to green, then yellow. Yellow means stop. So there is a transition of states. So we can also say that FSM in real life is the traffic light. Please change to the next slide. So as I have also mentioned that a real life example of FSM is traffic light. It goes from red it goes to green, and from green it goes to yellow. And another real life example of FSM is vending machine. In vending machine we insert coin, then item selected, and then we get the our desired thing as output. So it also goes from transition. Now, please next slide. Comes the more basic concepts of FSM. FSM is a combination of set of states and plus rules for transition. We have state A, and before state A we have the arrow, start arrow. Then from there the input or condition. Then state B, and from state B to state A it is also connected by other input. The machine is always in one state. Some states are final, accepting states. Input causes a transition to another state. One state is always the start state, and after the transition, when the final state comes, we can understand by the double circle. It means we have reached our final state. Here, please change to the next slide. So components of an FSM can be further divided into states, as we have discussed earlier. Input alphabet, transition functions. For example, sigma will start state and final state. Final state reached, and here our FSM ends. As it is a finite state machine, so our finite state machine ends in the final state.
Topic about the representing of the states. So Q0 is the start state, and Q1 is YOLO1 is the current state, and final state is represented by the double circle. And here and now we discuss about the representing the transitions errors between the states and label with the input that is the causes that input that causes the change. So Q0, it is the starting state. We start from here, and here to in Q0 we put the input 1, and then it goes to Q1. And Q0 input 0, it states in Q0, and then Q1 we put the Q1 input, and it states the self loop. It contains the self loops. And Q2 is the double represent the final states. The final state, that is the represent in the double circle. This is the slide number 8. Here we discuss about the how FSM finite state machine work in step by step. First which starts, machine begins in the start from state Q0, then read inputs, and machine reads the next symbol from input string, and then transitions. We find the next state and then machine moves to the new state, and repeat from the state, and last is finally string is accepted or rejected. This is the example of the if FSM accept string ending in 0 and 1. Here the two alphabet 0 and 1 accept for any strings ending with 0 and 1. So we started state is q0. It has the self loop 1, and it's from the 0 it goes to the q1, and it's after the input 1 it goes to q2, and then it is the accepted 0 and 1, and there are the q2 has input string 1, that is the goes to q0, and in and in q2 has the q0 input, that is goes to the q1. This is the slide number 10, where processing input 101, uh, q0 is the state where the beginning in the state, and step 1 হচ্ছে q0 in input 1, uh, q, q q0, and new state it states in q0, and q0 its input 0, it moves to the q1, and q1 is input 1, it goes to the q2, move to the q2, and then q2 is the final state, and it's accepted the string.
Uh, my name is Deepo Halder. I am presenting right now slide 11, state change visual walkthrough. Now let's actually watch how the FSM process and input string step by step. This slide shows a visual walkthrough of processing the string 1, 0, and 1 from Q0 to Q1, then finally Q2. Uh, First, we read the input symbol 1. According to our instruction rule, a delta of Q0 or start state of Q0 with input 1, input 0 here. Think of it like a lookup chart. Each row is a state and each column is an input symbol. The value in each cell tells if I am in this state and I read this input, where do I go? For example, look at state Q1, input 1. The table says Q2. That means if you are in Q1 and you read A1, you move to Q2. And the start symbol marks the final or accept state, that's Q2. So this table is just a compact way of writing everything that those arrows in the diagram represent. Next slide, please. Okay. Let's now trace through a slightly longer example, the string 1001. Our FSM is designed to accept any string that ends with 0, 1. So 1001 should be accepted. Since it does end with 0, 1, let's verify that. We start at Q0. Step 1, we read 1, rule delta of Q0. 1 equals Q0. We stay at Q0. And step 2, we read 0. Rule delta of q0, 0 equals q1, we move to q1. Then in step 3 we read 0 again, rule delta of q1, 0 equals q1, we stay at q1. Then step 4 we read 1, rule delta of q1, 1 equals q2, we reach q2, which is our accept state. So the string 1001 is accepted. The machine correctly identified that it ends with 01. This is the power of FSM. It can check patterns in string automatically. Next slide, please. Okay. Now we get to a very important concept, the difference between two types of FSM and DFA, deterministic finite automaton. The key property uh, is no ambiguity, only one possible path of any input string. And at the look at the diagram, the input ABC takes us from Q0 to Q1 to Q2 to Q3, and there is one path and only one path. This makes DFAs very predictable and easy to implement in code. You can use a simple variable to track the current state and a switch case to handle transitions. DFAs are widely used in compilers and logical analyzers, the part of a compiler that reads the code and identifies keywords, variables, and operators. Okay, now we are non-deterministic FSM. Uh, the second type is non-deterministic FSM. In a NFA, for a given state and input, there can be more than one possible next state. As you look at the diagram where we are at Q0 and read A, the machine can go to either Q1 or Q3, either Q1 or Q2. Two choices. Now you might wonder, how does it decide which path to take? The answer is, it's likely the machine guesses the best path. If any path leads to an accept state, the string is accepted. Compared to a DFA has one path and is simpler to implement. An NFA can have multiple paths but is more flexible to design. Here's the most important point on this slide is every NFA can be converted into an equivalent DFA. So they recognize the same kinds of language. We just sometimes prefer one form over the other. And that wraps up my part of the presentation. I will hand over this to my next friend. Thank you. Sir, am I audible?
Yes.
Okay. Can I please go to next slide? It is great question of Deepo. Please next slide. Okay, so your topic is state combining. That means minimization. Here we are combining similar states. If two states behave the same, we can merge them into one state. In this example, Q1 and Q2 have the same transitions, and both are non-final states. So we merge them into a single state called Q1 plus Q2. This process is called FSM minimization. It reduces the number of states and makes the machine simpler and faster. Please here go to next slide. Now it is conversion of NFA to DFA. Here we learn the steps to convert from NFA to DFA. First start with NFA. Second, list all possible state combinations. Third one is each combo becomes one DFA state. Fourth one is build new transition state. And fifth result is equivalent DFA. Key inside subset construction and NFA in multiple states at once becomes one combined DFA state. Example, NFA in Q1, Q2 simultaneously, DFA has a state called Q1, Q2. DFA may have more states, but it's fully deterministic. Here, go to next slide. Here we learn application of FSM. Finite state machines are used in many real-life applications. In compilers, they have a lexical analysis to identify tokens. In game development, they control character behavior like walking, attacking, or dead. In networks, they are used in protocols like TCP states. In UI design, they manage page flow and form validation. In digital circuits, they are used in flip-flops and counters. In pattern matching, they are used in regex and searching. So FSMs are everywhere in computer science. Go to next slide, please. So it is advantages of using FSM. FSMs have many advantages. They are simple and easy to understand. They are predictable. Same input gives same output. They are efficient and fast. They are easy to debug because we can track each state. They are easy to implement in code and they have strong mathematical foundation. So FSMs are very useful in system design. Next slide, please. So to summarize, FSM is a model with finite states and transitions. At a time, only one state is active. DFA has one path per input, while NFA can have multiple paths. Both can recognize the same type of languages. FSMs can be minimized to reduce states. Also, NFA can always be converted into DFA. FSMs are widely used in many applications like compilers, games, and circuits. Next slide, please. So it is my gate question. Given a language L, define Li as follows. L to the power 0 is epsilon. L to the power I is equals to L to the power I minus 1 for all I greater than 0. The order of a language L is defined as the smallest case such that L to the power k is equals to L to the power k plus 1. Consider the language as L1 over alphabet 0 accepted by the following automaton. So the order of L1 is asked here. So here accepted strings are epsilon because first step is accepted state. So it can accept anything. So accepted strings are epsilon 0, 0, 0, 0, etc. So L1 is epsilon union 0 to the power odd. Now L1 square is L1 into L1 and we know odd plus odd is equals to even includes all length. So L1 square is equals to 0 star. So L1 3 is equals to L1 square into L1 is equals to 0 star. So L1 square is equals to L1 3. So here order is 2. Next slide please. So thank you sir.
Thank you. Very good presentation by you.
Of an FSM. So here we can understand there are main 5 types of components of an FSM, that is the state, input alphabet, transition function, start state and final state. As we have understood that how can we understand that we have reached our final state? By understanding there is a concentric circle. So now we are heading towards our next slide. So here is our gate question. Given the language L equals AB, AA, BAA, which of the following strings are in L star? Options are given and it is a multiple correct option question. So now here we comes that L star means the clean star. So means you can concatenate 0 or more strings from L in any order and any number of times. So L star equals all strings formed by joining the given here options are AB, AA, BAA. So here are 4 types of combinations and we can partition those by our given options. AB, the first option AB partitioned plus AA plus BAA plus AB plus AA. Now comes the second option AA plus AA plus B double A plus AA. Now here cannot be partitioned because using AB, AA and BAA there will be no partition. Now comes the fourth option BAA, partition on the basis of BAA plus AB plus AA. So now our correct option is C now our correct option is C as it cannot be partitioned as a combination of strings in set AB, AA and BAA. Thank you.
In this presentation, we will cover its basic idea and components. So, now I will begin with the introduction of Turing machine. A Turing machine is a mathematical model of computation. It works on an infinite tape and follows a set of rules to process symbols. Basically, it helps us understand what a computer can and cannot compute, which makes a foundation of modern computing. The concept was introduced by, So the concept was introduced by Alan Turing in 1936. Later it became the foundation of modern computer science and Charles Turing thesis. Even today it is used to define computability and complexity in computer science. The basic idea of a Turing machine includes 3 main parts: infinite tape, which acts like memory; read or write head, which read and write symbol; finite control, which decide the next step. So overall the machine reads a symbol, writes a new one, moves left or right and changes state. Now coming to the core components. Tape stores input and acts as memory. Head reads and writes symbols. State register keeps track of current state. finite control the logic of transitions. These components work together to perform commutation step by step. That's all from my side. Thank you.
Okay, so please change the slide. So, sir, this is the formal definition for Turing machine. The main all the symbols are given here. Like m is equals to the first symbol states about q, which is known as the finite set of states. Then is sigma, which is the input alphabet, which is symbol including blank. Then it is tape alphabet, then it is delta, which is transition function. Then q naught, which means an initial state or a start state. Then b, which is also equal to a tape alphabet, which is blank signal. And f means set of accepting or final states. So please change the slide. Now the transition function. There is a small equation to it that delta of q comma x is equals to p comma y comma d, where q stands for the current state as per previous slide. Then x denotes symbol currently read, and p is next state to enter, y is symbol to write, and d is direction to move, which is left or right. The transition function completely determines how the machine processes input and transforms the tape. So please change the slide. This is how a Turing machine works. First, it reads the file, which is head reads symbol at current tape position. Then it writes that new symbol written to current cell. Then it moves it. Head shifts left or right by any cell. Then transition. As per the previous slide, we know that how much transition function is helpful to us. State changes according to transition function. This cycle repeats until the machine reaches a halting state, at which computation stops and result is determined by the final tape configuration. Change the slide. This is the visual representation of a Turing machine. The first is tape configuration, infinite tape with symbols arranged in cells, and then initial input appears in consecutive cell surrounded by blank symbols. Then head position. Arrow or pointer indicates current cell being processed. Head moves dynamically during execution. Then it's the state diagram, which is circle nodes represent states. Arrow shows transition labeled with read, write, or move operation. Just right. This is the example problem to it. This is only an example which the problem statement is determine whether a binary string contains an equal number of zeros or ones. So how can we approach it? We can approach it by using Turing machine. Turing machine can mark pairs of zeros and ones systematically, eliminating one of each until only blank remains, which is accept, or unmatched symbols remain, which mean reject. This demonstrates how Turing machine can solve non-trivial computational problems through careful state design and tape manipulation. Like as an example, we give input which is 001, which will accept equal counts like two zeros and two ones, and it will reject the another input which is 0001, which is unequal count because it has three zeros and one one. Please change the slide. So now my partner Sneha will continue.
Yes, sir. Good evening, sir. My slide will start from understanding the Turing machine. So Turing machine is a theoretical model of computation which is introduced by Alan Turing. It helps us to understand how machines solve problems and process information. So Turing machine form the foundation of computation theory. Next slide, please. There are types of Turing machine. So there are different types of Turing machine like deterministic, non-deterministic, multi-step, and universal Turing machine. Next slide. Here is the difference between deterministic Turing machine and non-deterministic Turing machine. In deterministic Turing machine, only one move is possible at a time, and in non-deterministic Turing machine, multiple moves are possible at the same time. Next slide. Here, universal Turing machine. So, a universal Turing machine can simulate any other Turing machine. It is a basic idea behind modern computer, and also it receives the description of any Turing machine plus its input data. Next slide. There is the application of Turing machine. Uh, in different fields, like Turing machines are used in language recognition, problem solving, compiler design, and artificial intelligence. That's it, sir.
Bhavan, please start.
Bhavan, please carry on.
Okay, so Turing machine versus finite automata. So it basically tells us the differences that clarify how Turing machine is more powerful than computation models. So whether about features, power, tape, direction, computation classes. For Turing machine, it has infinite tape available for finite, and for finite automata, it has finite memory only. And Turing machine is more powerful than finite automata, and as well in Turing, it is read and write cases, and in finite automata, no tape, only states are there. And in Turing machine, you can move left or right, and finite automata only forward transitions available. Recognizes in recursively innumerable languages, but in finite automata, it recognizes regular languages. Change the slide. Change the slide. Yeah. So church Turing. So church Turing thesis. Any function that is effectively computable can be computed by Turing machine. Okay. So the fundamental principle of the computation theory is independently by Alonzo Church and Alan Turing. So it represents the limits of what we have computed by mechanical process, and the theses were unproven widely by the computer science and theoretical basis for understanding compatibility and complexity. Change the slide. There are four advantages such as powerful computational model, algorithm simulation, theoretical foundation, and versatility. Next. The limitations, there are three limitations, which are practical implementation, where the designs are not real world computing. It requires infinite memory and impractical to build physically. The performance is extremely low and complex for practical problem. And undecidability, some problems cannot be solved by any Turing machine. Change the slide. So there are two problems which we have solved for the gate questions, like which one of the followings are equivalent to the following assertions. M decides the language, L subset of 0 and 1 star. So the correct statement will be option D, which is the explanation is given over here, which is the computation for Turing machine decides the language, which must follow the two conditions, which is acceptance and rejections. It must enter the accept state for every string that belongs to the language. As well, it must enter a reject state or halt state for every string that does not belong to the language. Change the slide. Okay, so another MCQ is there, which is which are undecidable. So as we can going through all the options for A, it is undecidable as checking if two TMs accept the same language is equivalence problem, which is known to be undecidable. Okay, and the B is also undecidable due to Rice's theorem. C is also undecidable because universality problem, and D is decidable because in 1073 steps, TM behavior depends on finite prefix. So we can check all these cases. Okay, next slide. So the key takeaways are theoretical backbone, computational limits, and still relevant. And next slide. Thank you.
So let's start with the first slide. Our topic is Mealy and Machine. So yeah, this is the title. Now, starting with the first one, introduction to transducers. So today I will present on transducers. We know that DFAs and NFAs are decision machines that accept or reject strings. Transducers are different. They generate a continuous sequence of output symbols while reading the input, because the main goal is to continuous mapping. These machines do not have final or accepting states. The two main types are Mealy and Moore machines. Then let's look at the Mealy machine. The main feature is transition dependent output. The output is generated during the transition between states. It depends on both the current state and the current input symbol. The mathematical definition uses a lambda function as seen on the slide. Lambda maps the combination of states and the input alphabet to the output alphabet. On the diagram, output are placed on the transition arrows written as input slash output. Now, the definition leads to a specific behavioral characteristic. First, there is no spontaneous output. A transition is strictly required to generate an output. Second, that input string and the output string are exactly the same length. A 5-letter input gives a 5-letter output. Third, the machine has an immediate reaction. The output is determined the moment the input is applied. Finally, a Mealy machine is very efficient. It generally requires fewer states than a Moore machine to perform the same task. Now, moving on to the example slide. So here is an example of a Mealy machine. The task is to design that a machine that outputs a 1 for every occurrence of substring ABB starting at the state Q0. Receiving an A moves the machine to Q1 with an output of 0. Receiving a B moves it to the Q2 state with an output of 0. Receiving one more B completes the ABB pattern, moving to the machine back to Q0 with an output of 1. If the input string is AABABB, the machine processes it step by step and gives the final output of 00001. So now coming to the next gate level question of Mealy machine. So the statement 1 says the last bit of output depends on the start state. This is false. If the machine receives a long string of ones, it will always end up in the state S2 and output as 0. So that is that. And for statement 2, for statement 2, reading a 1 from any state forces the machine into the right of the diagram, either S1 or S3. For either S1 or S3, reading another 1 guarantees we end up in the state S3. So for the statement 3, the output is 1. The final input must be 0 coming from state S2. The only way to reach S2 from the state S3 with the input 0, so our sequence ends in 0, 0. Finally, every single transition leading into S1 or S3 requires an input of 1. By tracing backwards, we have proven the sequence must be exactly 1, 1, 0, 0 to get the 1 output. So the statement 3 is also true. Therefore, since statement 2 and 3 are both logically correct, the final answer is option 3. I will next pass on to Shovik, please.
So, good evening, sir. I will briefly explain the Moore machine. Is a type of a finite state machine where the output depends only on the current state, not on the input. This means each state has a fixed output. One important feature is that it produces an output at the initial state, even before any input is given. Because of this, for an input of length n, the output length becomes n plus 1. Next, move on to the next slide, please. So another point is that Moore machines have a slight delay because the output is generated only after the machines moves to the next state. So they are more stable and predictable, but may require more states compared to Mealy machines. So overall, Moore machines are simply state-based systems with reliable output behavior. I'm directly going to the so uh, so here the gate questions asks us to identify which statement is false among four concepts. So here option B states that converting a Mealy machine to a Moore machine can result in at most m cross n states. So which is correct? For option B says a Moore machine can with n states can be converted to a Mealy machine with an most n states. This is also correct. Option D. Option D is based on subset construction for NFA to DFA conversion and it is valid. Option C is false because it incorrectly states that a DFA is equivalent NFA with up to 2 to the power n states. In reality, the opposite is true when converting an NFA to a DFA. The number of states can go up to 2 to the power n, not the other way around. Therefore, the correct answer is option C. So next slide will present uh, Sritoma.
Good evening, sir. Sir, in this slide, it has a difference between Moore machine and the Mealy machine, and we know that the states of Moore machine is more than the state of the Mealy machine, and the output string length for the Moore machine is n plus 1 as Moore machine except the first state, but for the Mealy machine it is n. Then I will go to the conversion portion. There are two types of conversion: Moore to Mealy machine conversion and Mealy to Moore machine conversion. For this, if we can draw a diagram for Moore machine, we can easily convert with Mealy machine, and vice versa is also true. Now the next slide is Mealy to Moore machine conversion. For this slide, the present states and A is the start symbol, and the next state for the I0 and I1 are the input. For the present state A, and after accepting the input symbol I equal to 0, it is going to the next state D and output is 0. And for I equal to 1, it is going to B and the output is 1. And for the present state B, after accepting the input I equal to 0, it is going to the next state A and output is 1. And for I equal to 1, it is going to, after accepting input string I equal to 1, it is going to the next state D and the output is 0. And for C and D also are same. And here I will also tell one thing, that C is the trap state, because from after in C present state, if I accept I equal to 0, it will go to next state C and the output is 1. And for I equal to 1 input string, and from present state C, it will go to next state C also, and the output is 0. So here we can tell the table that for the next state A, we are getting only the output is 1. So A1, A0 is not possible, and for D is also same, D0, D1 is not possible. And for B, B next and output is 1, and B next output 0. And for C, that is also so, B0 and B1 and C0, C1. So there are two type of steps. And for A1, if we accept the input string 0, so from directly A1 we are going to D0, next state D, and output is 0. And if we go to D, then I0, and we are going to next state B and output is 0. And then for B, I0, next state A and output is 1. So if we check the 1 from after in present state A, after accepting I1, it will go to next state B and output is 1. So in this way the total process will be done. But in C it is trap state, so from in A, B or D, from any state it will not go to C. So then I will go to the next slide, move to Mealy machine conversion. Here we know that the steps which are in the Mood machine, that the number of steps will be less in the Mealy machine. So for present state Q0, next state is Q0 Q1, and the output is A. And for Q1 next state 01, it is going to Q2 and Q0, and output is B. And for Q2 output is C, and after accepting the input 0, it is going to Q1 state, and accepting input 1, it is going to Q2 state. According to question, it is that. And here this is the picture. And here we can directly go to Mood machine to Mealy machine. So Q0 and for the Q0 output is A, so Q0 output A, and 1 output is B. For Q1, after accepting 0, it is going to next state Q2, and for Q2 output is C. And Q1, and for present state Q1, after accepting input string 1, it is going to Q0 state, and for Q0 state output is 1, and for Q2 that is also same. Then I will move to the get question. In this question, it is the answer will be option B, because here if we consider that the first slide for the 01 answer will be option A, because if we consider the option B, it will not accept it, because the 01 output is 0. If we get output 01, then first 1 and then 0. And for C, it is also rejected. But for A, if we take the 01 output, then first 1 is 0, then it is 1, so we are getting 01. And then for the 10 output, we are getting 1 input. First input is 1 and second input is 1, so it will be 10. So the final answer is option A. Then we will go to conclusion slide. Here we can tell that there are two type of machine, Mealy machine and Mood machine. So Mealy machine is faster than the Mood machine, and Mood machine is slower. And in Mealy machine there are less number of steps, and Mood machine there are more number of steps. So that is, thank you.
Will be presenting on finite state machines, a fundamental concept in automata theory that helps us understand how systems process input and change states. A finite state machine, or FSM, is a model that works with a limited number of states. It reads input step by step and changes from one state to another. We can see FSM in real life, like traffic lights, vending machines, and even password validation systems. So abstract model is about process input, pattern recognition used in languages, and foundation used in advanced machines. Formally, an FSM is designed with 5 components. Please change this slide. So it is designed with 5 components. Q is the finite set of states. Sigma is the alphabet. Del is the transition function, and Q0 is the initial state, while F is the set of accepting states. Please change this slide. No, keep the previous slide. So alphabet means the set of inputs and that the machine reads. A string is the set of accepted string. A language is the set of accepted strings. Transition means moving from one state to another. FSM, next. Hello, next please. FSM are classified into 2 types, with output and without output. Without output examples are DFA and NFA. With output are Mealy and Mood machine. DFA is deterministic finite automata, which has only one path, while NFA has multiple paths. So that's it for me. Now Ahun will continue.
Good evening, sir. So there are Mealy and Mood machines. These are machines where the finite state machine gives an output on a certain input. The Mealy machine works where the FSM gives the output depending both on the current state and the input symbol. So with the change of the state, the output can change as well, even if the input remains same. And then there is the Mood machine. Mood machine is same as Mealy machine, but here it is independent of the stage. The output is hence fixed with changing state as well if the input is same. Then we have the deterministic finite automation. So DFA, it is deterministic because particular there is a particular output, fixed output on certain fixed rules which are called transitions. In deterministic finite automation, there can be exactly one transition per state input pair. So these are always fixed. The sigma here cannot be zero. The power of sigma cannot be zero. That is, the length of the string should at least be one, and it cannot be infinite as well. So DFA is rule based, and it is the most simplest form of finite state machines. Then there is a non-deterministic finite automation. The difference with non-deterministic finite automation with DFA is that here many transitions can be possible from the same state input pair. It can be 0, 1, or even more than that. Um, in NFA, there is a possibility that a zero power sigma transition, that is epsilon transitions, can happen where there are no inputs, where there are no input symbols. It is easier design because there are fewer states required sometimes, because there are zero epsilon transitions possible. So there are fewer transition states required, which makes the design much more simpler than DFA. Uh, and the transition function map each state symbol pair a set of possible next state. Thank you, and the next slide will be continued by Arunjit.
I will be saying the FSM processing workflow. Every FSM process follows the same fundamental circle, that is the start in the initial state, consume input signals at a time, and update state after every symbol. Lastly, we have to evaluate the finals. This cycle repeats after every signal's input. Acceptance is determined solely by whether the machine's standard level finds out the processing of the last symbols. Next, we have the DFA versus NFA key distinctions. Firstly, we have the transition behavior. The DFA, which is the single deterministic path for every single input, and NFA, which is the multiple computations path, can be exit simultaneously. Conversation, the substrate constructions methods symmetrically converts any NFA into a equivalent DFA. Representation method, here we have the state diagram, transition table, and the formal specifications.
Okay, so this slide, it mainly explains how an FSM decides whether a string belongs to a language or not. So there are certain conditions. First, we start from the initial state, that is Q0. We read the symbols one by one. We follow transition, and if we end in a final or accepting state, then that string is valid. Otherwise, it is an invalid state. So the example we used here is even number of zeros. So in this situation, we make Q0 as the initial state and also as the final state. Because since even number of zeros, then epsilon is also a valid string. So we read 0, switch between Q0 to Q1, we read 1, say in the same state. So for example, if we take string 010, we start at Q0, read 0, go to Q1, read 1, stay at Q1, read 0, go again to Q0. Since Q0 is the final state, therefore it is an accepted string. It is a valid string. So the next slide. In here we see about the NFA to DFA conversion. So the main idea is the NFA can have multiple possible next states, but the DFA cannot. So there is a simple method. Each DFA state is a set of NFA states. Let's say NFA is in state A, B. Then the DFA treat that as one single set. Important point to be noted here is if an NFA has n state, the DFA may have up to 2 power n states. Many states may be unreachable, so we remove the useless states. Part 2 of this is DFA minimization. Our goal is to reduce the number of states without changing the language. We use group equivalent states and equivalent behaviors. Every regular language has one unique minimum DFA. Go to the next slide, please. In this slide, we are doing an example. First, we divide the states into initial and non-initial. Sorry. First, we divide the states into final and non-final states. One is a final state and rest are non-final. So we divide them. State one is accepting, others are non-accepting. And the second part is 2 and 5 behave the same. That's therefore they are grouped together. And 3 and 4 behave same. Therefore they are grouped together. So there are three distinct groups. So we have minimized the DFA from 5 to 3. Important point to be noted here is if there are equal number of zeros and ones, the language is not regular since the DFA has finite memory. Okay, my part is done here.
In this question, there is an example of finite state machines. In the present state, we can see A and C, A and F are having a simple next state, that is the x0, x equals to 0 and x equals to 1, where if A considers FB and F considers FB, so we can get an F as an one state, and next we have the B and E as another state and DH as another state, and as an unique output we get C and G. So total there will be 5.
Okay, so as the question says that the string should be started with 1 and it can be ended with 0 and 1. So the first option is cancelled because it is started it has the string 1 0, so it is not accepted. The next option B is also cancelled because it is started with 0, which our DFA rejected, and option C is accepted because it is started with 1. Option D is also rejected because it has the string 10 and 110. So that's why C is the correct option.
Yes, the next question is about a Boolean expression, and it's about the minimization of the DFA. So here we use simple De Morgan's law. As we know, the complement becomes like A plus B complement becomes A complement or B complement. So in the given function, we have x bar, y bar, z bar plus x, y bar plus y, z bar. So we take y bar common from the first two term, and we get x plus x bar z bar, and then another term y z bar. So we use the property a plus a complement b becomes a plus a complement dot a plus b. Hence, the function becomes x y bar plus y bar z bar plus y z bar. Again, we take z bar common from the last two term, and we get f is equal to xy complement plus z complement y plus y complement. As we know, y plus y complement is equal to 1. So we get the final answer, f is equal to xy bar plus z bar. This is using the distributed process. We can write f bar is equal to z complement plus x into z complement plus y complement, which is the minimization form of the DFA.
Studying,
we are going to, প্রেজেন্টে করতে পারবো না 30% চার্জ আছে আমার
we
ল্যাপটপে
are going
ল্যাপটপে চার্জ না দিলে হয় কারেন্টটা দে না ভাই প্লিজ কারেন্টটা দে
এই এভরিবডি দেয়ার কে বলছে এটা তো
Okay, so our topic is Chomsky hierarchy and in automata theory and formal language. So in this slide, I'm just introducing the topic. Chomsky hierarchy is a classification system that divides language into 4 types based on rules and computation power. It is very important in understanding how programming languages and compilers are work. So in this slide, this is an overview of our presentation. So I will briefly overview the presentation. We will first understand what formal languages and grammars are. Then we will study the 4 types of grammar step by step from simplest to most powerful.
Okay, Ajit, slide 3, please. So here comes formal languages. Alphabet. Now, what is alphabet? Alphabet sigma means a set of symbols, just letters like 0, 1 or A, B. A string means a sequence of symbols like 0, 1, 1, 0 or A, B, B, A. A language means a collection of strings. Now, grammar means a rule system that generates strings. It is written as G is equals to V, T, P, S, where V is variable, T is terminals, P is productions, and S is start symbol. So simply grammar means rules to generate valid strings. Now, goes to the slide 4. Okay, so here, moving to the next slide, here we can see that a production rule is there that alpha produces beta, where alpha is a left side element and beta is right side. It is the replacement, and we are going to replace alpha, and the replacement is beta. So it means replace alpha with beta. And if I give example, S produces A is B or S produces AB. Using these rules, we generate strings step by step. This process is called derivation or produces. Here the key terms like sentential form, sentence and leftmost derivations, which replace the leftmost variable first. Next slide, slide number 5. Okay, background. Okay. Slide 5. Huh. Noam Chomsky. Here the comes Noam Chomsky, about Noam Chomsky. Noam Chomsky is the scientist who introduced the hierarchy in 1950s. His work is the foundation of modern computer science. Today, it is widely used in compilers and programming language. And for him, we are now studying Chomsky hierarchy. So from slide 6, please slide 6. Yeah, so here we can see that there are total 4 types of Chomsky hierarchy according to the diagram. Type 3 is regular, type 2 context free, type 1 context sensitive, type 0 is unrestricted. Here comes the relation. We can see that type 3 is the subset of type 2 is the subset of type 1, and type 1 is the subset of type 0. Here, one another thing, here subset means content in. So I mean to say that type 3 content in type 2, content in type 1 and content in type 0. Every regular language is context free, but not all context free languages are regular. As we go upward, power increases and complexity also increases. So from the next slide, I would call Ajijuddin to present.
Hello.
Yes, carry on,
So
please.
as she says, the Chomsky classification is divided into 4 parts. So we start with the regular grammar, which is type 3. So there is basically one rule here that the the string should be simple, and the type 3 grammar is the simplest grammar in among this all. Like type 2 and type 3 is more complex than type 3, and the finite automation is the machine is used here to recognize the values, as you can say. And here the example for regular grammar is string like b a b or a, you can say aab. And application of regular grammar, you can say the pattern matching. Why is the pattern matching? Because in regular grammar there is no type of memory, so it can't count. That's why it is used for simplest tasks. After that, we have context free grammar, CFG. So context free grammar is more complex and more powerful than type 3 grammar. Here basically one rule we have to remember, that the left side always there is a single variable. And here push down automaton PDA is used for the machine as recognize the value of this grammar because there is a stack. So the PDA, this machine can remember these values, and you can say there is a string S goes to A as B. So the values is looks like nested. That's why it is used for compilers to understand the syntax. That's why it is more complex than type 3 grammar. After that, we have type 1 context sensitive grammar, CSG. Context sensitive grammar is more complex than previous two, and here the string is you can say example a to the power n, b to the power n, c to the power n. This is more these types of grammar are used to recognize the values is used to linear bounded automaton LBA. LBA because here we can't use PDA to solve these types of problem, and that's why it is more complex, and the application of these types of grammar is bioinformatics, DNA pattern matching. It is more complex than previous tools, that's why it is used. After that, we have more most complex grammar, which is unrestriction or rules there for recognize these types of grammar, and these types of grammar we can't recognize by PDA or LBA, so we use Turing machines to solve these types of problem. And you also can say these types of grammar is a theoretical model of a modern computer. So this is a most application of unrestricted grammar. After that, we have the comparison table. So you can say the grammar here. You can see unrestricted, context sensitive, context free, and regular. Type 1, type 2, type 3, and type 0. The machines are used for regular grammar is finite automaton FA. After that, context free grammar is push down automaton, and context sensitive grammar is used LBA, which is linear bounded automaton, and unrestriction type 0 is used for Turing machines. Regular grammar is used for classes, which is regular languages. Context free grammar is used here, context free languages, and context sensitive grammar used context sensitive languages, and unrestricted grammar is recursively innumerable languages. After that, we have finite automation, which is Surajit will explain the next tasks slides.
Okay,
Surajit,
come on. Surajit.
Okay, coming to slide number 12, we have finite automaton. This is the simplest machine in the hierarchy, and it recognizes type 3 languages. It operates with a finite set of state and moves between based on input symbols. The most important point here is here is no external memory. It can only remember which state is currently in. As shown on the slide, we have DFA, that is deterministic, and NFA, non-deterministic. DFA and NFA have the same power, and NFA can be converted into an equivalent DFA. Next slide, Ajit. We move to the push down automaton or PDA. A PDA is essentially a finite automation with an added stack. The stack provides last in, first out, that is called LIFO, allowing the machine in push and pop symbols. Now looking at the types of DFDA and NFDA, NPDA, DPDA and NPDA, deterministic and non-deterministic. NPDA is more powerful than DPDA. There is some context-free languages that DPDA cannot recognize, which is why NPDA is the standard recognized for this class. Next slide, Rich. Turing machine, the most powerful model in hierarchy. It uses an infinite tapes as its memory and read-write head. The head is highly flexible. It can move in both direction, left and right. It can also change symbols on the tape. According to the Turing thesis, this machine can simulate any logic that a digital computer can perform, making it the ultimate mathematical model of computation. Next slide. Closure properties. This tells us if a language stays in the same category after a specific operation. Regular languages are closed under almost everything, like union, intersection, and complement, etc. However, context-free languages are not closed under intersection or complement. This means if I take the intersection of two context-free languages, the result might not be context-free. Context-sensitive and recursively languages also have their own specific closure rules at listed in the table. That's all. Now, Sumit.
Yes. So my topic is parse trees and ambiguity in CFGS. So there are parse tree for A plus A into A, grammar E plus E by E is into E by A. And now unambiguous grammar fixed. Enforces precedence before plus E equal to E plus T by T. So here T equal to T into F by F. CNF, Chomsky normal form. Every rule is either A two variables or A one terminal. All CFGA is convertible to a CNF. CNF used in CYK parsing algorithm. Pumping lemma for CFL if L is context free. Any long enough string in L can be pumped. Next slide please. And there is regular expression and regular languages. So there are regular expressions, algebraic notation for describing regular languages. A symbol, it matches exactly A. Then second one is empty, matches empty string. Third one is R plus S union, matches R or S. Fourth one is RS, concat, matches R then S. Fifth one is clean, 0 or more R prime S. And last one is R plus 1 or more R prime S. Then REFA, regular grammar, all equivalent. Number one is RE2 NFA Thompson's construction. Second one is NFA-to-DFA subset construction. Third one is DFA to RE state elimination method. And fourth one is all three define exactly regular languages. There are some examples. Theta plus the last one is real world application for Chomsky hierarchy. There are 12 fourth type 3 regular, type 2 CFG, type 1 CSG and type 0 TM. In type 3 regular, there are basically 5 main functions: lexical analysis, grep or regex engines, third email or URL validation, fourth network firewall rules, and fifth search and replace tools. For type 2, compiler parser, second one XML or HTML or JSON parsing, third Java or C or Python syntax, fourth mathematical expressions, fifth SQL query parsing. For type 1, natural language syntax, context aware cinematics, Third one is bioinformatics or RNA. Fourth one is some AI language models. And last one is bounded computation. And for type 0, computability theory, then algorithm complexity, then AI decision problem. Fourth one is halting problem proof. And last one is cryptographic proofs. This one will be for engine.
Okay, let's summarize the key results. These are the decidability and undecisibilities of the entire topics we have stated about. This is the comparison table as we have seen. So I would like to come to the next slide because all this we have covered before. Okay, now let us conclude let us summarize the full topic using these three gate previous year questions. The first one is identifying the language type. In gate questions, we usually given this type of languages where we have to choose the pattern. So for these cases, if there is no counting, it is regular. That means type 3. If there is one counting, it dependency. The counting dependency like a to the power n, b to the power n, it is context free like type 2. And if there are multiple dependencies like a to the power n, b to the power n, c to the power n, it is context sensitive type 1. So the trick is more dependency means higher type. Next, move to the second questions, which is closure and DCFL. The task is to identify which are deterministic context-free languages. So L1 and L2 can be solved using a deterministic TDA, but L3 cannot because it needs guessing the middle point. So which requires non-determinism. So the correct answer is only L1 and L2. This question tests the difference between DPDA and NPDA. And the last question of latest question also 2024. Here we are given a context-free grammar in CNF, Chomsky normal form. A string W, the value is given. So we have to calculate the total length, and as it is calculated, the total length come 179. So this question is the understanding of CFG structure and derivation process. So I'd like to conclude the matter. Please, thank you, slide. Yeah. So to conclude the Chomsky hierarchy, it gives us a clear way to classify different types of languages based on their complexity and the computational models required to recognize them. By analyzing these patterns and dependencies in this language, we can directly determine its grammar type and the appropriate automaton. With this, we come to an end of our presentation. So, at the end, thank you so much, sir, for your time and attention.
Thank you. Very
Finite automata, DFA versus NFA, theory and conversion. So I myself, Kaushali Mukherjee, start to present this slide first. So in the next slide, Manish, please change the slide. In the next slide, we will cover the key differences and NFA to DFA conversion with the certain examples. So here is the main point, the automata theory. What is automata theory? It is a branch of theoretical computer science that studies the abstract machines and the problems they can solve. The key terms are computation, languages, machines. And in the Chomsky hierarchy, we see the finite automata places at the type 3 position in regular languages. In the next slide, we will talk about the finite automata. So finite automata is a mathematical model with limited memory. It works in 3 steps. First, it has a finite state of states. Second, it reads the input one symbol at a time from left to right. Third, it decides to accept or reject the string. If the machine ends in a final state after reading the whole string, the input is valid. So in the next slide, we will talk about the components of a finite automata. Let's take an example. Any finite automata M is defined by 5 parts called a five-tuple. Q is the finite set of states like Q0, Q1, Q2, and epsilon is the input alphabet like 0 and 1, and here is the delta is the transition function. It tells the machine where to go on each symbol. Example of Q0, 0 equals to Q1. Q0 is the start state where the processing begins. F is the set of final states. If we end here, the string is accepted. So from the next slide, Pritam will continue.
This next slide. Deterministic finite automata. Key property. For every state and every input signal, there is exactly state. No ambiguity, no choice. Total function, no epsilon transition, deterministic, always holds. Total function delta q into summation tends to q maps every to exactly one next stage. Deterministic finite cannot move without reading an input symbol. Deterministic, give the sample input. A deterministic finite automata always produce the same execution path. It always halts. A deterministic finite automata always terminates after reading all input characteristics. Please next slide. Please, Manish, next slide. Deterministic finite automata example. Starting ending with string b over a and comma b. Here Q0 is a initial state, and initial input is B, then tends to final state Q1. Here, if you initial input is B, then stay in Q0 state. Please next slide. Here step the input string AAB over deterministic finite automata accepting strings ending with B. Step 0. Start in initial state Q0. Step 1. Read input signal is string A, then stay in Q0 state. Step 2. Input signal is A, and then stay in Q0. Step 3. Input signal is B, then move to Q1 state. Next slide. Non-deterministic finite automata. Key property. For a given state and input symbol, there may be 0, 1 or multiple possible next states. The machine explode all paths simultaneously. Key difference between deterministic finite automata and non-deterministic finite automata. Transition state. In deterministic finite automata, one state only there. In non-deterministic finite automata, 0, 1 or multiple state is there. Transition, delta transition, not in deterministic finite automata, not allowed. In non-deterministic finite automata, allowed. Paths. In deterministic finite automata, single unique path. In non-deterministic finite automata, multiple parallel paths. Power. In deterministic finite automata, same by or equivalent. In non-deterministic finite automata, same or equivalent. Complexity. In deterministic finite automata, more states needed. In non-deterministic finite automata, compact representation. Some example of non-deterministic finite automata. Please next slide. Example of non-deterministic finite automata. Here, formal definition is input signal is Q0, input state 3 state Q0, Q1, Q2. Here, input transition state is Q0. If A is input signal, then stay in Q0 or Q1.
is input signal is B, then stay in Q0, and input signal is B, then move to Q2 state. If input signal is A, then move to Q2 state. If input signal is B, then stay in Q2 state. This next slide.
Paushali? And you have all forgot to put on your camera whenever you're speaking. Okay.
স্যার অ্যাকচুয়ালি পাওয়ার কাটের জন্য
ঠিক আছে, এখন
কারেন্ট নেই, যার জন্য ক্যামেরা
ঠিক আছে, ঠিক আছে। তাহলে তোমরা কি আরেকজন তো ওয়েট করছে, শুভঙ্কর কি আসবে কি আসবে না? অন্যরা তো রয়েছে না আরো দেয়ার।
So good evening everyone. Today my team members Rajdeep, Rahul, Priyam and Priyankshi, and I will be presenting on finite state machine in real life systems. This presentation is for our formal language and automata theory course, and we will be exploring how these theoretical models drive the technology we use every day. Of states and transitions, while it looks overwhelming, the core concept is simple. Systems move between various points based on specific rules. Let's break down exactly what that means. Introduction to FSM. So, what is a finite state machine? It is a mathematical model of computation where a system exists in exactly one state at any given time. Transitions between these states are triggered by external events or inputs. For example, in this diagram, input A causes a transition from state 0 to state 1. This logic is the foundation for digital logic, software compilers and network protocols. Next slide, please. So definition of FSM. Mathematically, an FSM is defined by a five-tuple Q, sigma, delta, Q0 and F. Q represents the set of all possible states the machine can occupy. Sigma is our alphabet or the set of all valid inputs. Delta is the transition function that maps a state and an input to the next state. Q0 is our initial starting state, and F represents the state of final or accepting states where a process successfully ends. Next slide, please. The history of FSM. The theory has deep roots, starting in 1943 with McLuhan and Pete's neural network models. In 1950s, the field expanded rapidly. Stephen Klein introduced FSM theory in 1951, followed by George Mealy and Edward Moore, who proposed the two primary machine models we use today. By the late 50s, Robin and Scott introduced non-deterministic models, eventually leading to FSMs being standard in hardware and software design by the 1970s. Let's look at the actual building blocks. States are the distinct conditions like a machine being idle or running. Transitions are the rules that define how we move between those states. Inputs are external signals like a button press or a sensor trigger. Outputs are the action produced. Depending on the model, these happen either during a transition or while inside a specific state. Finally, we have our initial state to start the process and final states to indicate completion. Next slide, please. To test our understanding of these properties, let's look at the technical problem from GATE exam. The question asks which statements regarding regular languages are true. The correct answers are C and D. This is because if a language is not regular, its complement is also not regular. Additionally, regular languages are closed under union and complement, meaning if you combine them or find their opposite, the result remains a regular language. So next.
Priyankshi will take on.
Yeah, so finite states of machines are based on transitions. A state represents in a specific
condition of a system and only one state can be active at a time. A transition is a movement from one state to another triggered by an input or event. Input are external signals like buttons, presses, sensors, values. Next slide, please. Networks events that triggers transitions. Outputs are the actions produced by the system, such as displaying a message or turning on a device. Next slide. In a Mealy machine, the output depends on both the current state and the input. This means output is produced during the transition, making it faster and often requiring fewer states. Next, please. In Moore machine, the output depends only on the current state. Output are associated with states instead of transitions, which makes the system more stable. State diagrams are used to visually represent FSMs. Circles represent states, arrows represent transitions, and double circles indicate final states. They help us clearly understand how the system behaves. Where sigma star R1, sigma star means all possible strings over the alphabet. So sigma star R1 means all strings are not in R1. This is the complement of R1. Since R1 is regular, its complement is also regular, so that statement is true.
Moore machine, presented by me, Shubhajit, Shreyanka, Shatarupa, Rahul, and Shuham. So, what is Moore machine? Moore machine is a type of system where the output depends only on the current state, not directly on the input. This makes it very stable and predictable. Before understanding the Moore machine, we need to understand several topics. So, before understanding the Moore machine, we need to understand some several topics. First is combination circuit and sequential circuit. Combination circuit, the output depends only on the current state, and there is no memory. So, the system does not remember any past input. But in sequential circuit, the output depends on both the current input and the previous state. That means this circuit have memory element like flip flop. That's why this circuit can perform some complex tasks like counting, pattern detecting, etc. Another one is finite state machine or FSM. Is a consist of a finite number of states and it charts from one state to another state based on input. It has four main components. One is states, inputs, outputs, and transition. There are mainly two type of FSM. One is Moore machine, another one is Mealy machine. In Moore machine, the output depend only on the current state, but in Mealy machine, the output depend on both the current state and the input. Because of this, Moore machine are more stable since the output change only at a specific time. So, now we can start.
Okay, sir, I'm starting now. So a Moore machine is a finite state machine where output depends only on the current state. The output changes only when the state changes. So it is stable and predictable. Next slide, please. So it has 6 components: Q states, delta is represented to input, then delta is represent to output, and lowercase delta is present to transition function, and lambda is represent to output function, and lastly q naught is represent to initial state. The machine changes state using delta lowercase and produces output using lambda. Next slide, please. Formally, actually it is written as m is equals to states, then sigma, delta, delta lowercase, lambda, and q naught. Output depends only on the state. So, and the example is a parity checker shows whether the number of 1 is even or odd. Next slide, please. So, this is a block diagram. the input goes to the state register and the output is generated from the state only. So the output does not depend directly on input. This gives stable and glitch-free output. So next, Shranka will continue, sir.
So, am I audible?
Yes, you're audible. Please carry on.
This slide introduces the visual language used to map out a Moore machine. Each circle represents a discrete state the machine can occupy. In a Moore machine, the output is labeled inside the circle, signifying that the output is tied strictly to the state itself. The arrows indicate the path between states triggered by specific input symbols labeled on the arrow. The double circles are used in language recognizers to identify accepting or final states. Unlike other models, the output is never placed on the transition arrow. It is always associated with the destination state. Next slide, please. This slide demonstrates how the visual diagram is converted into a structured mathematical format. The table lists the present state, the input, and the resulting next state. Crucially, the output column depends only on the present state and not on the input received. A Moore machine is formalized as a six-tuple. The design is synchronous and glitch-free by nature because the output only changes when the machine moves to a new state at a clock edge. Next slide, please. This slide transitions from a theory to a concrete example of a Moore machine in action. It illustrates a system designed to detect a specific binary sequence within a stream of data. The slide emphasizes that for sequence detection, Moore machine provides stable outputs that are tied directly to the progress made in recognition of the pattern. Next slide, please. This slide breaks down the design of a machine specifically built to find the sequence 101. The machine uses 4 distinct states to track its progress. S0, the initial, the recent state where no bits have been matched yet. Output is 0. S1, reached the first one detected. Output still 0. S2, reached when 10 has been detected in order and the output is 0. S3, the success, reached only when the full 101 sequence is complete. The output finally goes high 1. Next slide will be presented by Shobha.
Good evening, sir. Now in this slide, we will be presenting how inputs change states. In a Moore machine, the output is tied to the current state, not the input. When the machine enters S3, the output immediately reflects the detection, regardless of what the next input will be. In the diagram, we can show and see it clearly. Next slide. Now the key differences between Moore machine and Mealy machine. Well, we have 4 main differences. Output dependency. Moore, it depends on state only. Mealy machine depends on state plus input. Timing. Moore outputs update on clock edges. Mealy can react mid-cycle.
Shobham, I already corrected in this one of the slides. It's not Moore, it's a Moore machine, please.
Oh, sorry, sir. Sorry, sir. State count. Moore typically needs more states for equivalent behavior. Glitch sensitivity. Mealy is more vulnerable to input noise. Next slide.
Not Mealy, it is Mealy. It is Mealy and Moore, not Mealy and Moore. Okay, carry on.
Okay, sir. Advantages of Moore machines. Stable, predictable outputs. Outputs change only on clock edges, eliminating mid-cycle glitches and race conditions. Simpler design logic. Output logic depends only on state variables, easier to minimize and verify. Glitch resistant. Input noise cannot directly propagate to outputs, making Moore machines robust to noisy environments. Next slide. Disadvantages of Moore machines. 1. More states required. Equivalent Mealy machine designs often need fewer states, increasing flip-flop count and hardware costs. 2. Output delay. Output changes 1 clock cycle after triggering input, a slight latency penalty. 3. Higher resource usage. Extra states mean more logic gates and potentially more power consumption. The next slides will be presented by Rahul.
Good evening, sir. I will be explaining the applications of Moore machines. Moore machine is a finite state machine where the output only depends on the current state and not on the inputs directly, which is already stated by my friends. So I will be explaining some of the key applications of Moore machines. For example, the first example which is given here is the traffic light controllers. So here each light represents a state. There are three lights we know: red, yellow, green. These all state that which light will glow, that is fixed for each state. Now the changes occur only when the clock and time interval occurs. So this system is very stable. So for example, when the state is S0, that is red, then red is on, the red color is on. When the state is for S1, then green is on. When the state is S2, the yellow color is on. Now for the second example, that is a vending machine. We have the same function overall, that there are states and there are outputs. The state represents the amount of money that is inserted in the machine, and the output, that is the amount of item that will be dispensed from the vending machine, which happens to be have a specific state when it is reached. So for example, if you give 0 to 5 rupees or anything in the machine, that it will give us a product out of the machine. So this is another example. Now the third example we can see is that the sequence detectors, which is actually used in digital communication and error detection. Then which detects patterns like binary bit stream. It is. Sorry, sir. I got. So let me continue. And this is how the sequence matching occurs in the sequence detectors. Next slide, please. So the designing of the Moore machine, here we have got 4 steps. That is how to defining the problem, which will actually clarify and identify our inputs, outputs, and what is the expected behavior we'll get from the Moore machine. The step 2 is identifying the states. So we will break down the system into minimum number of states, so that it is easy and frequent to us for to understanding us. So each state will represent a unique condition in each case. The drawing of the state diagram is very much important, as it emphasizes on the images and give us a more clarity. So the uses of circle for states and arrow shows the transition between the input and the output. So these are all the things we need in that state diagram. Now the creating of the state table, which is most important. So in the state table, we know there are which inputs the output. Next slide, please. Now the implementation of flip-flops and logic gates, which is a hardware realization. Now once the design is ready, we implement using digital circuits. So for example, S0 equal to 0, S1 equal to 1, S2 equal to 1, 0 in binary. And now the flip-flop selection occurs in D flip-flop, which is a simple flip-flop, and for JK flip-flop, traffic signal. Yes, sir. The traffic signal system and the takeaways we get from it. So I have already explained the working of the traffic signal. So I will not get into details. The state are red, green, yellow. That is stop, go, and wait. And in between the transitions occur. So this is all for this slide. Next slide, please. So we have questions from Moore machines.
Carry on, carry on.
শুভজিৎ মিউট আছিস, আনমিউট কর।
Consider a finite state of machine with one input x and one input f, represented by the given state in a transition table, and the minimum number of states required to realize the FSM is the given table: present state, next state, and output. Now come to the answer explanation. By checking the given transition table, we can merge B and E and D and H. Then the result FSM will be below. For the present state, these are all the present state, next state, and output. And now again, in the above FSM, we can merge the state A and C, and then the final FSM will be five state, which is AC, BE, DH, F, and G, and representing the next state and outputs. Another question: consider the following two languages over the alphabet A and B, and L1. This is the equation of L1, and this is the equation of the L2, and these are the four options. Which one is correct? For the definition of L1, which is this equation alpha, beta, alpha. Alpha belongs to A and B, and the beta belongs to A and B. So this is the equation of L1, and for L2, alpha, beta, gamma, and this alpha belongs to alpha and beta belongs to A, comma B. This is the equation of the L2. In the summary, L1 requires recognition pattern that standard finite automata cannot compare, rendering it non-regular, and L2 involve a construction that a finite automata can merge, making it regular. Rahul, take this question.
Please unmute Rahul, then please start.
Sir, am I audible?
Yes,
Hello.
please audible. Carry on.
So sir, the next question we got, that is there we have got a 5-state NFA with the epsilon transitions shown in the figure. So if we go by the options, we see the regular expression. For the first example, the string there is 0, 1, 1, which is not generated by the regular expression, so we can eliminate this option. Now if we go to option number D, that is the regular expression is 0. This includes the empty string which is not generated by this regular expression, so we can also eliminate this example. Now going to the option number C, the string 000 is not generated in the regular expression here also, so we will eliminate this option. Now the last option which is remaining, which based on the counter examples and the analysis, we get that is 0 plus 1 0 0 1 1. So option number B is correct in this question. Thank you, sir.
Okay, good night. Very good. Next group, please.
Sir, I am presenting now because the current was gone. We have to look for.
No, you are the only one who are left.
Now, me and Rahul is left.
Okay, please wait. Others, they are in a group. So this is, I am very sorry for this. Let the whole group who are waiting.
Sir, our group is present. I am presenting now.
Sir, we were allotted an earlier slot, so can we start?
No, that's it is our runtime. So who are the first four are present? Please start. Please wait.
Start.
Who the all four are there right now? Please start.
Yes, sir.
I am
Sir,
we. So there is everybody at his home. So I can take your presentation till night. Don't worry. I will take all the.
Sir, I am presenting now.
Okay.
Start, Shubhajit.
Shubhajit. Group 3 of.
Everybody
group
should present
2.
with the camera. Those who the camera can on, they first present. Who else? Then they. Otherwise, you have to wait. Let
Again,
the four
Shubhajit.
persons who can on their camera.
Sir, camera isn't working. Sir,
Why?
wait for
I have
one.
told you. Come from mobile. Mobile camera is working. Front camera. Why is the problem? Other can.
Okay, sir. I am sharing screen now. I am opening from mobile
Why
also.
you are sharing? Your camera is not working. Why you are sharing the screen? The other three are there. Everybody has laptop. Why you take the burden? Why you don't have all the features? I have told you, no, all the features. Okay, please carry on. Night is enough. Carry on without cameras. Please start. Shubhajit, please start.
Okay, sir. We are presenting the equivalence of DFA and NFA. I am presenting the slides of the DFA. Okay.
Shubhajit, at least make it a
So the
presentable.
table of contents, we'll first learn the introduction to
Shubhajit,
the finite automata.
Shubhajit,
Yes,
Shubhajit,
yes,
please
sir.
make it as a
Hello.
presentable mode, not as a page by page mode. Make it is a presentable.
Okay, okay,
F5, yeah.
okay,
Start from
okay.
beginning, yes,
So,
please.
I am starting with finite automata. Okay, so a finite automata is an abstract mathematical model
Your
of
screen is not
computation that.
moving. Your screen is not moving. You make have to be presentable, not this. Yes.
Sir, now moving.
It is moving, but
Hello.
not in the presentation mode.
Slide share mode, bro. Slide share mode.
Slide share, what is F5 or just tell from your get your from you should know all these things.
Sir, the screen share
Okay.
isn't working.
Okay,
Network is.
everything is not working. Your camera is not working. Nothing is. You have to make a software for it. Okay, whatever you can, you start beginning. Everybody is
Sir,
refrain. Yeah.
so at first I am sharing what is finite automata. A
No, start
finite
from beginning.
automation
Start from
and
beginning. Start from beginning. First screen. Please. Okay.
okay, I am presenting equivalence of DFA and NFA. So in this topic, I will start from the finite automata. Then my group mates will present all other determinist. I will present also the deterministic finite automata. Then Shruti will present non-deterministic. Then DFA versus NFA means deterministic versus non-deterministic finite automaton, and then the equivalence theorem, and then the subset constitution algorithm, then the working examples, and then applications and summary. Okay, so in the finite automata, we'll learn about the finite automata, which is an abstract model of computation that process a string of input symbols and decides whether to accept or reject it. Okay, we will denote the states as q, which finite set of configurations in the machines that can be denoted as q, and the summation sign, which denotes the alphabets. The transition modes is represented by the delta, and the start state is denoted by q naught, and the accept state is denoted by f. Then the deterministic finite automation, the formal definition of it, we can define it by a five-tuple format, like I have shared it earlier. Q if the summation sign, then del, then q naught and f. Okay, uh, in the deterministic finite automata, for every state q, there belongs capital Q, and the symbol A belongs to the whole set of the one. Okay, exactly one next state is defined for one, and there is unique states, and for the single path, any input string, there is exactly one computation path through the automation. The total function del is defined as all combinations of the states and input symbols, no missing transitions, and no epsilon moves means DFA cannot make transitions without reading an input symbol. Means if there is a phi state, we can no if there is a epsilon state, we cannot transition to the next state. In the DFA, transition diagram and table. In the example of DFA, when we are taking an input, okay, so it's an starting state as the arrow is sending to Q naught. We can see there is two inputs, 1 and 0. Okay, exactly one inputs. When we are taking 1, we return it to Q. When we are putting it into the transition table, we can see Q naught goes to Q1, and when we are inputting 0, it goes to Q1, and when we are inputting 1, it goes to Q naught itself. Okay, and then for Q1, we can see there is 0, which returns to Q1, and when Q2, we run 0 and 1s, it returns to itself. Okay, so we can understand like this. for one state, one single term, we return to one single state. Then how I have explained it earlier, how does the DFA accept or reject a string? Machine begins in the start state queue, as I have told. Then read input symbols one by one from the left to right. We are going to left to right, and if we want to see it right to left, then we will have to mirror the whole thing. Then transition, applying delta current state symbol to get the next state. Okay, if we go give 1, it returns to q naught, its next state, and if we again input 0, then it will return to the q1. So in the end, after all inputs is consumed, we can check in the final state. Okay, the accept or reject if state epsilon accept or else reject. Then my fellow mate Shruti will continue with the next slides of non-deterministic finite automation.
Hello. Sir, am I audible?
Yes, yes, you're audible. Please.
Yes. Sir, this is the 7th slide of the presentation. Non-deterministic finite automation formal definition. An NFA is a 5-tuple where n equal to q sigma delta q naught f, where q sigma q naught f same as DFA. And there are key properties of NFA such as multiple choices. Delta QA can return Q1, Q2 or more, 0, 1 or more, many next states. Parallel paths, NFA explores all possible paths simultaneously like a superposition of computations. Epsilon transitions, the machine can move to a new state without consuming any input symbol. Acceptance rule, a string is accepted if any one computation path ends in an accept state. Next slide. Then NFA transition diagram and table. Here Q naught, if in Q naught there is 0, 1, it will return to Q0. And if there is 0, it will return to Q1. And in Q1, if there is 1, it will return to Q2. Then we have the table like state. If it's Q naught, in input 0, it will give Q naught and Q1. In input 1, it will give Q naught, epsilon will be null. In second state, Q1, input 0 will be pi, input 1 will be Q2, and epsilon will be null. In Q2, input 0 will be Q2, in input 1, Q2, and in epsilon, it will also be null. Next slide. DFA versus NFA key differences. Here properties are transitions. In DFA it is exactly one next state. In NFA it is set of states 0, 1 or more. Epsilon transitions in DFA it is not allowed. In NFA it is allowed. Computation paths in DFA single deterministic, NFA multiple parallel. Acceptance is final state must be in F. NFA in any path ends in F. Property state count typically larger up to 2 to the power n states. In NFA, smaller, more compact. Expressive power in DFA is regular languages. In NFA, regular languages same. Ease of simultaneation is in DFA is easy to implement. In NFA is harder to implement directly. In the property of ease of design, DFA is harder to design, and in NFA easier, more intuitive. Next slide. Yes, it is the 10th slide of the presentation. It will be equivalence of DFA and NFA. Here, when DFA is to NFA trivial, every DFA is an NFA where transition element always returns a singleton set. In second property, NFA is to DFA. In trivial requires the set construction power set algorithm. And in third, consequences, regular languages are closed under both middles. In the last step, consequences. If a language is recognized by NFA, it is also recognized by DFA. Thank you, sir. Next slide.
Good evening, sir. I am Yuvraj Srivastav. Sir, am I audible?
Yes, yes, please go.
Okay, sir. Subhajit, please.
What happened?
Sir, just a second. My teammate is not presenting the screen, so just for. Okay, sir. Yes, he's doing.
But it is so small. You are checking for mobile. Mobile is not allowed for the desktop.
Shruti, can you do it,
Technical
please?
glitch.
Yash, can you? It is from yeah. Shubhajit.
Yes. Okay. Okay. Okay, sir. So yeah.
So I was facing network issue from the beginning, so it was getting problem. Now I have fixed the problem. Okay.
Okay, okay, okay. Thank you, thank you. Okay, sir. So I am presenting slide number 11. So yes, sir. We begin explaining how to systematically convert an NFA into a DFA. Uh, the main idea is that our
Juboraj, who
new.
is speaking? Juboraj, who is speaking?
Yes, sir. Yes, sir. I am Yuvraj Srivastav.
Okay, okay, fine. Carry on, please.
Okay, sir. Thank you, sir. Yes, sir. So the main idea is that our new DFA will simulate all possible parts of the NFA simultaneously. So since as we can see, an NFA can be in multiple states at once. So a single state in our new DFA will actually represent a set of NFA states. This is why the set of the DFA is the power set of the all NFA states. So the start state of our DFA is simply a set containing the NFA's original start state. So finally, for any acceptance of a DFA state that contains at least the one NFA accept state becomes an accepting state in our new machine. So Subhajit, please next slide. Yes, sir. So now NFA to DFA conversions with the epsilon transitions. So we expand to handle the NFAs that include epsilon transitions. So that which moves the machine makes without reading any input symbol. To do this, we introduce a concept which is called epsilon closure, which is used to include the states still plus every other state it can reach just by following the epsilon arrows. When we build our DFA, we have to apply this epsilon closure to our start state at that moment. We also apply it after every single input symbol is read during the transition function. This ensures that that our DFA can be accurately capture all the parallel branches the DFA might take without consuming the input. So Subhajit, please next slide. Yes, sir. So here I am presenting the subset construction algorithm. Which puts this concept into a step-by-step programmable format, which we start by initializing the DFA with the epsilon closure of the NFA start state. Then we use a loop to process each state and for every possible input, we find all reachable NFA states and calculate their epsilon closure to form the next DFA state. And if this newly formed state hasn't been seen before, we add it to our list of states to process, and which in which the algorithm perfectly translates any NFA to a DFA. So Sojit, please next slide. Yes, sir. So now the closer, the key building block, in which we dive a bit deeper into the epsilon closure, which is truly the like a main part of this conversion process. Uh, by defining the epsilon closure of a set of states is all the NFA states you can reach from them using only epsilon moves. To compute this, we can use a simple stack-based approach, and we push our starting states onto a stack, pop them off one by one, and follow any epsilon transitions. And if we find a new state, we add it to our own closure state and push it onto the stack to check its neighbors. So thank you, sir. And now from yes, we'll continue.
Good evening, sir. So I think I'm audible.
Yes, yes, you're audible. Carry on.
So, sir, this is Yash Pandey, and now I need to continue with the slides to come. So, as already discussed about the subset construction algorithm problem, so to make this more concrete, we have got two worked out examples. The first problem that is given to us asks us to construct a DFA from the given NFA transition table that has been provided. Label table is 3.27. Now it contains states which are Q0, Q1 and Q2, whereas the second problem asks us to do the same for the NFA represented by the transition diagram in the provided figure. So let's discuss the solutions. Please turn to the next slide. So let's look at the solution for the first example. First of all, when we apply the subset construction method, our new DFA states are literal subsets of the NFA state set. Okay, as you can probably get to see. Now, first of all, we start with the initial subset, which is Q0, and look at the input A. The NFA transitions from Q0 to both Q1 and Q3, as you can see in the table. So our new DFA state becomes the subset Q1 and Q3. Now, if we input B from the start state, we transition to Q2, Q3, and then we chart out the reachable states for A and B for each newly discovered subset. And this has to be done until and unless our transition table is complete and no new subsets emerge. So this is how the entire process has been carried out from beginning to the end. Please turn to the next slide. Now moving on to the solution for the second example, so which is based on the diagram. Once again, we have to establish our start state as Q0. We evaluate the transitions to find new reachable subsets, which are Q0 and Q2 and Q1 and Q3. The most important So the most important takeaway from this process is that we only include the subsets that are actually reachable from the start set. That is important to consider. This ensures our resulting DFA is as compact as possible while still accepting the exact same language as the original NFA. So this is how the question has been done, and this is how it can be well furnished and well structured all throughout. Next, move to the gate question that's there to the next slide. So now we have a very beautiful question which is from GATE CSE 2003. So to see how this theory is tested, let's look at a question from this GATE exam. Okay. So we are given a specific deterministic finite automaton, as you can see, and asked to find how many 7-bit binary strings where the first, fourth and last bits are fixed as 1 are accepted by the machine. So once we analyze the DFA, we know it accepts any string containing the substring 001 that has been provided in the question. Now we can break this into two valid cases based on where the 001 is formed. Case 1 yields 4 possible strings and case 2 also yields 4 possible strings. Now when we subtract the first string, the only string that overlaps between both cases, we get a total of 7 valid strings. And this makes C as the correct answer after particular evaluation and further calculations. Okay. Next we move to the applications which is there in the next slide. Please turn to the next slide. Now let's understand where is all this that we are studying actually used. So equivalence of DFAs and NFAs is foundational to computer science, as we have already got to know in our study till this juncture. In compiler design, lexical analysis relies on it to quickly tokenize source code. First of all is tokenizing source code. It's the engine behind text search patterns, as already mentioned. It is also used in natural language processing, and that too in spell checkers. And regular expression engines like Python's RE module, regular expression module, also utilizes it in its function. So beyond software, it's also used to formally verify network protocols and minimize hardware states in digital circuit design. So please move to the next slide. So to finally wrap up, let's summarize the key takeaways. A DFA requires exactly one next state and is straightforward to implement, as already understandable. Whereas an NFA can return a set of states and is easier to design conceptually. So one thing is I think very much prominent, that despite these differences, they are identical in computational power. Both recognize regular languages, but we are bridging the design simplicity of the NFA and the implementation efficiency of the DFA using the subset construction algorithm. So with this, I conclude our presentation, and thank you all of you for listening. I think, sir, you must have liked the presentation as a whole. Thank you.
Very good. Thank you. Yes, your gate question is great. Good. Carry on. Next group, please, who are all present.
Sir, can we present?
Sir, can we start?
Only one of you. Please decide yourself.
It's the same group, sir. Same
Okay.
group, sir.
Okay.
Same
Please.
group, sir.
Please. Please present.
Krishna. Okay, sir. Now I am start.
Make
Today, my team and
please,
sir,
please
sorry.
start, please.
Hmm. Can you say, sir? No.
Please start, please. No issue.
Today, my team and I are here to present our project of deterministic finite automata, or DFA. This is a core concept in the subject of formal language and automata theory. Krishna, next slide. Next. So this is the content page. Next slide. Next. So introduction. So introduction to automata theory. What is automata theory exactly? It is the study of abstract machines and the computational problems they can solve. It provides the mathematical foundation for things we use every day, like compilers and AI. In the Chomsky hierarchy, DFS belongs to type 3, representing the simplest form of automaton, the finite automaton. Next, please. Now is what is DFA? A DFA is a model that reads an input string on symbol at a time and returns a definitive accept or reject answer. It is deterministic because every state and input has exactly on defined next step. There is no ambiguity. It is finite because it has a fixed number of states and cannot use unlimited memory. Essentially, it's an automatic processor following predefined rules. Next slide, please. This formal definition, the five-tuple. Mathematically, a DFA is defined by a five-tuple. So there is a Q, sigma, delta, Q0, and A. Q is the set of states, sigma is our input alphabet, and delta is the transition function. Q0 is where we start, and F is the set of accepting states, where the machine halts if the string is valid. All the five components must be specified for a valid definition. Next, my friend Datta will present. Somati Datta.
Good evening, sir. Am I audible?
Yes, please.
Now let's look closer at these components. Q for states. Q states represents the memory configuration of the machine and is shown as circle. The alphabet contains the valid symbols like 0 and 1. The transition function must be a total function, meaning it is defined for every possible combination of state and symbol. Finally, accepting states F are shown in double circles. Next slide, Krishna, please. Now transition function, delta explained. You can think of transition function as the brain of the DFA. It takes your current state and an input symbol to give you a unique next state. For example, delta q comma a equal to p means in state q, reading a move on top, move on p. It is a total and deterministic, meaning there is exactly one output per input. Next slide, Krishna. Now state diagram DFA visualization. Visualize, Visuals make DFAs much easier to understand. We use a start arrow to show the initial state Q0 and double circles to mark accepting states. Next slide, Vishnu. Now transition tables. If you prefer a mathematical layout, we use transition tables. It is a matrix where rows are states and columns are input symbols. This is useful for programmers because it can be easily implemented as a 2D array in code. Arrows indicate the initial state and asterisk indicates accepting states. Now my friend Motto will present.
Sir, am I audible?
Yes, yes, you are audible.
Okay, sir. Good evening, sir. I'm going to explain a DFA which accepts string with even number of zeros. First, let's understand the language. The language consists of all binary strings, that means strings made of 0 and 1, where the number of zeros is even. Here, even includes 0 as well. Now let's look the states. We have two states in this DFA, Q0 and Q1. States. State Q0 represents that the number of Q0s seen so far is even, and it is the accepting state. And state Q1 represent that the number of Q0s is odd, and it is a rejecting state. Next, the transitions. Whenever we read a 0, the state changes. That means if we are in Q0 and read 0, we go to Q1. If we are in Q1 and read 0, we go back to Q0. But when we read 1, the state doesn't change. So from Q0 on input 1, we stay in Q0, and from Q1 on input 1, we stay in Q1. This happened because we are only counting the number of Q0s, not ones. Now let's take an example. Consider string 1001. We start from Q0, reading 1, we stay in Q0. Reading 0, we move to Q1. Reading another 0, we go back to Q0. Reading 1, we stay in Q0. Since we end in Q0, and which is an acceptance state, the string is accepted. So next slide. The I already explained this slide in previous. So next slide. The DFA works on binary strings. The DFA accepts strings ending in 0, 1. This DFA works on binary strings, meaning the input symbol are 0 and 1. However, now I will explain the states used in this DFA. There are three states, Q0, Q1 and Q2. State Q0 is the starting state, and state Q1 represent that the last symbol read is 0. And Q2 represent that the last two symbols are Q1. And it is the accepting states. Now I will explain how to transitions work. From Q0, if we read 0, we move to Q1. From Q0, if we read 1, we stay in Q0. From Q1, if we read Q0, we stay in Q1. From Q1, if we read 1, we move to Q1, which means we found 0, 1. From Q2, if we read 0, we go to Q1. From Q2, if we read 1, we go back to Q0. Now let's take an example. Consider the string 1001. We start from Q2. Reading 1, we stay in Q0. Reading 0, we move to Q1. Reading another 0, we stay in Q1. Reading 1, we move to Q2. Since we end in Q2, which is the acceptance state, the string which is accepted because it ends with Q, 1. Next slide. Transition table and step-by-step trace, which is explained in this previous slide. Next slide. Extended transition function. The extended transition function del star generates del to process complete string, not just single symbols. It is defined recursively and gives a state reached after reading an entire string W. And the best case is del star in transition of Q and epsilon equals to Q. Reading epsilon leaves the state unchanged, and there's a recursive step del star Q and WA, and del of del star Q W comma A. So next slide, and Krishna will explain this.
Good evening, sir. Now I will explain the real life example for DFA using a traffic light. A traffic light works exactly like a demonstrative finite automation because it has a fixed number of states and follows a predefined sequence. Here the states are red, amber and green. The input is time signal which tells the lights when to change. The system always starts at the red state and the transitions are fixed. Red goes to amber, amber goes to green and green goes back to the red. This deterministics because at any point there is only one possible state next state. For example, from red it must go to amber. There is no alternative. We can consider green as per accept state, meaning go. So this simple traffic system clearly demonstrates how DFA works in real life. Next, now it's look to some important application of DFA. First, in compiler design, DFA is used for lexical analysis. It helps identify keywords, variable and symbols from source code. Second, in pattern matching and regular experience, DFA is widely used in tools like text editors and search engines to efficient find patterns. Third, in network protector, DFA modules define connections states like listening, sending and assembled connections, etc. Fourth, in digital circuit design, sequential circuits such as controllers and traffic systems are designed by using DFA concepts. Fifth, in input validations, DFA helps validate formats like email address, phone numbers, and URLs. Lastly, in bioinformations, DFA is used to analyze DNA and protein sequence. So DFA plays a crucial role in many areas of computer science. Now I will compare DFA with NFA. In DFA, for each states and input symbols, there is exactly one transitions. But in NFA, there can be 0, 1 or multiple transitions. DFA does not allow Epsilon transitions while NFA does. DFA does not require backtracking, but NFA may require it. In terms of acceptance, DFA follow the fixed path, where NFA accepts if any path leads to final states. DFA is harder to design, build, easier to implement. NFA is easier to design but need conversation to DFA implementation. Both DFA and NFA have same experience power, meaning they recognize the same class of language. Also, any NFA can be converted into equivalent DFA using a subset construction method. So overall, DFA is more practical or implementation, while NFA is more flexible for design. And now finally, it summarizes the key points of DFA. A DFA is defined by 5 components: status and input symbols, transition functions, initial states and accepting states. It process input strings step by steps, always has unique next state, making it deterministic. DFA recognize regular language which are also known as type 3 language. It is time to complexity is linear, which makes it efficient and easy implementation. However, DFA has limitation. It cannot handle language that requires memory, such as context free language. Also, NFA can be converted DFA using the subset constitution method. In conclusion, DFA is powerful and widely used model in areas like compiler, pattern matching, networking, and digital system. Now, Bhatto is explain the gate questions.
Yes, sir. Here we are given language L over 0 and 1 such that all strings must end with the substring 0, 1, 1. So our goal is to identify which DFA accepts exactly those strings that end with 0, 1, 1 and rejects all the others. To solve this, we think in terms of tracking the last few characters. First, we wait for a 0, then we accepted 1, then another 1. So the DFA should move step by step like start 0, then 0, 1, and then 0, 1, 1. Now we check each option. Option A, because it is wrong, it accepts string ending with 111, not 011. Option B also wrong because it accepts many string not ending in 011. Option C, it even accepts string like 1111. And option D is true because it accepts only those string ending with 011. So option D is correct. And next slide. Uh, in this question, we are given a language L such that the string shouldn't contain three consecutive ones. So that means 0 and 1, 1, 1, 101, and 110 is allowed. But 1, 1, 110 or 1, 1, 0, 1, 1, etc. It is not allowed. So we need to design a DFA that tracks how many consecutive ones we have seen. We create states like Q0, Q1, Q2, and Q3. Q0, if we reach Q3, it is rejected and all other states accepted. So total the validated states are Q0, Q1, Q2, and Q3 is dead state. So option B is correct, 4 steps. Next slide.
Let's
So
start.
can we start?
Yes, yes, please start.
So good evening everyone. Today my team members Rahul, Priyam, Priyankshi and I Rajdeep will be presenting on finite state machine in real life systems. This presentation is for our formal language and automata theory course, and we will be exploring how these theoretical models drive the technology we use every day. So to begin, the complex looking diagram represents the intricate nature of states and transitions. While it looks overwhelming, the core concept is simple. Systems move between various points based on specific rules. Let's break down exactly what that means. So introduction to FSM. So what is a finite state machine? It is a mathematical model of computational where a system exists in exactly one state at any given time. Transitions between these states are triggered by external events or inputs. For example, in this diagram, input A causes a transition from state 0 to state 1. This logic is the foundation for digital logic, software compilers, and network protocols. Next slide, please. So, definition of FSM. Mathematically, an FSM is defined by a five-tuple Q, sigma, delta, Q0, and F. Q represents the set of all possible states the machine can occupy. Sigma is our alphabet or the set of all valid inputs. Delta is the transition function that maps a state and an input to the next state. Q0 is our initial starting state and F represents the set of final or accepting states where a process successfully ends. History of FSM. The theory has deep roots, starting in 1943 with McCulloch and Pete's neural network models. In 1950s, the field expanded rapidly. Stephen Klein introduced FSM theory in 1951, followed by George Mealy and Edward Moore, who proposed the two primary machine models we use today. By late fifties, Rabin and Scott introduced non-deterministic models, eventually leading to FSM being standard in hardware and software designed by the 1970s. Next slide, please. Let's look at the actual building blocks. First, states are the distinct conditions like a machine being idle or running. Transitions are the rules that define how we move between those states. Inputs are external signals like a button press or a sensor trigger. Outputs are the actions produced. Depending on the model, these happen either during a transition or while inside a specific state. Finally, we have our initial state to start the process and final states to indicate completion. To test our understanding of these properties, let's look at a technical problem from GATE exam. The question asks which statements regarding regular languages are true. The correct answers are C and D, because if a language is not regular, its complement is also not regular. Additionally, regular languages are closed under union and complement, meaning if you combine them or find their opposite, the result remains a regular language. Next, my friend Priyanshu.
So, finite state machines are based on states and transition. A state represents a specific condition of a system, and only one state can be active at a time. A transition is the movement from one state to another triggered by an input or event. Next slide. Inputs are external signals like button presses, sensor values, or network events that trigger transitions. Outputs are the actions produced by the system, such as displaying a message or turning on a device. Next slide. In a Mealy machine, the output depends on both the current state and the input. This means output is produced during the transition, making it faster and often requiring fewer states. In the Moore machine, the output depends only on the current states. The outputs are associated with states instead of transitions, which makes the system more stable. State diagrams are used to visually represent FSMs. Circle represents states, arrows represents transitions, and double circles indicates final states. They help us clearly understand how the system behaves. Now, there is one gate question. Let R1 and R2 be regular sets defined over the alphabet sigma. Then, as sigma stars is equals to R1, sigma star means all possible strings over the alphabet. So, sigma stars R1 means all string not in R1. This is a complement of R1. Since R1 is regular, its complement is also regular. So, the statement is true. Now, Priyam will continue.
Am I audible?
Yes, you're audible.
Okay, I
Please,
guess.
please.
Okay, so why FSM is important in real life? Because FSM is predictable because it have same input always gives same output, and it is also simple than other system like Turing machine, and it is also friendly for hardware and software design. And finally, it is safety crucial, means it is used in aviation and medical devices, which is important for a nation. Now I will explain a example, that is traffic light system. So okay. So this is a most basic real life example of SFM. It has three states: red,
that is for stop, green for go, and yellow for caution. Transition happens using a timer input. It follows a cyclic pattern. That is, first it will go to red, then green, then yellow, and then again red. So it is actually a Moore machine, that is, that output depends only on current state rather than input. So now, wait. So this is a gate question similar to traffic signals. So in this question, we have given the turn on speed of green light, yellow light, and red light, and the clock time. So here it is done, we calculate the total time. So we divide it by the clock cycle and we get the number of cycle. Then by using 2 to the power n formula, we find the number of flip-flop used. That is here 5 for this particular question. So now I will explain another machine, that is vending machine. So it starts in the idle state. When a user inserts a coin, it moves to the coin input state. Then the user selects a product and the machine checks if the amount is sufficient or not. If the condition is satisfied, then it moves to the dispense state and gives the product, followed by returning any change if applicable. If the user cancels the operation, the system returns to the idle state from any stage. This is the example of how FSM handle multiple conditions and transition effectively. So finally, I will explain the elevation system, which is another example, which is more complex than the previous two. It has states like idle, moving up, moving down, and door open. When a user presses a float button, the system firstly checks the current floor and decides which direction, up or down. After reaching the desired floor, the elevator opens the door. So it uses hierarchical FSMs where multiple smaller FSMs works together, one for movement, one for door control, and one for safety. This makes the system efficient and reliable. So now Rahul will present further. So Rahul.
Sir, am I audible?
Yes, please carry on.
Okay. Let's continue another real life example of FSM. ATM machine. Let's start with an ATM. When you insert your card, the machine moves from ideal to card in. You enter your PIN, it check it. If it correct, you pick a transaction. Once done, it eject your card. If you enter the wrong PIN 3 times, the card get seized, and after it, if you take too long, it reset back to the ideal. Every step is a state, every action is a transition. That's FSM in real life. Change the slide. Now washing machine. A washing machine goes through a fixed stages: fill, wash, rinse, spin, done. It only moves to the next stage when the condition is met, like water level reach or timer done. If something goes wrong, door opens or water fails, it goes to the error state. Simple step-by-step control using FSM. Change the style. Automatic door system. Automatic door, when a sensor detect motion, the door open. After a timer, it start closing. If someone comes in while it closing, it goes back to the opening. If there is an obstacle, it stop for safety. Each of these reaches in a state transition. Next step. Now let's discuss the gate question. Here let be an NFA with n states. Let k be the number of state in a
minimal DFA which is equivalent to n, which one of the following necessary true. So we know that DFA will be a subset of the set state of equivalent NFA. So the maximum number of state of equivalent DFA of an NFA will be 2 to the power n, where n is the number of state in NFA. As a set with n times has maximum 2 to the power n subset. So the answer should be k less than equal to n square. Can you the slide? Now in conclusion, so FSM are not just theory, they run system we use every day, like ATM machine, washing machine, like automatic door sensor, doors, traffic light. They keep things predictable and easy to use or easy to manage. That's the real value of finite state machine. Here the reference where we. Thank you, sir.
Thank you. Very good presentation. Next
Thank you,
group
sir.
who are
Sir,
waiting
can we
for long.
continue?
Yes. Please leave and next
Sir, can
group.
we start group 7?
You decide amongst yourself. I cannot judge you. Next, who are waiting for the maximum? Just please tell me.
Yes, sir. Raj will present your screen.
Yes. Our group number is 7 and our topic is NFA and DFA. Pratik will start. Pratik.
Yes, sir. Am I audible?
Yes, audible. Please.
So, I am Pratik Roy. So, today we are going to present our topic Automata Theory, NFA and DFA. This presentation covers the fundamentals of finite automata, differences between DFA and NFA, their conversions,
Where is your camera?
and real.
Where is your camera?
Oh, sir. Okay.
Okay, start. Start from beginning.
Okay, sir. So, screen tap present.
Yes.
So, so today we are going to present our topic Automata Theory, NFA and DFA. This presentation covers the fundamentals of finite automata, differences between DFA and NFA, and their conversions and real-world applications. So now, what is finite automata? A finite automata is a simple computational model that reads input symbols one by one and changes its states accordingly. It has limited memory, meaning it only remembers its current state. So remember current state. At the end of the input, if it reaches the accept state, the string is accepted. So next slide. So a formal definition of DFA. DFA is defined by 5-tuple Q set of states, sigma input alphabet, delta transition function, Q0 start state, S accept state. So for every input, there is exactly one transitions. Next slide. So here DFA example, here DFA accepts strings ending with A. The machine moves between state based on input symbols and accepts only when final state condition is satisfied. So next. So here is a DFA processing example. Let's take input 1011. The DFA processes each symbol step by step and finally reaches an accept state. This shows how DFA works deterministically with only one path. So Rajini, please move the gate question. So here is one of the gate question. So here is a question of gate question. Here is a five-state DFA. So which of the following statements is false? Here we have to determine. So when we try this DFA picture, minimize this DFA, we can notice 3 and 4 have same inward and outer transaction. We have to solve this question, we have to see which states are distinguishable and which are indistinguishable. So, so states 2 and 4 are distinguishable because they have different transitions from state 1. So in final minimized DFA, we can see clearly that there is 3 state 1, 2, 4 for only given strings with equal numbers of 1s and 0. So it will be accepted by DFA. So option B and C, these two are false. So Rajnil, please continue.
Yes, thank you. So next part is introduction to NFA. So basically an NFA is like a DFA, but more flexible. It transitions functions, returns a set of states instead of just one. This means at any point, the machine can be in a multiple states at once. It accepts a string, even if one path through those state ends in an accept state. Think of it as a machine.
Your camera? Front
Yeah,
camera?
1 minute, sir. Yes, it accepts a string even if it ends in an accept state. Think of it like a machine that guesses a right path or runs all paths simultaneously. So next we have the difference. So both machines recognizes exactly the same languages, that is, the regular languages, and are equally powerful. The difference is a style. A DFA is strict, one state, one path, no ambiguity, first to run, whereas a NFA is flexible, multiple paths, epsilon moves, easier to design. The smart approach is design with NFA, then DFA for execution. Next, we have the parallel computation, that is the NFA branching concept. So when the NFA reads a symbol, such as here it's given A from the state Q0, it doesn't pick one path. It splits into 3 simultaneous paths, leading to Q1, Q2, and Q3. Path 1 dies, later path 2 continues, but path 3 reaches and accepts it. Since at least one path accepts the NFA, the non-string, this is the core power of non-determinism. Next, we have the epsilon NFA, that is a null transition. So an epsilon transition is a free move. The machine jumps to another state without reading any symbol. The epsilon closure of a state is all the states reachable from its epsilon moves. For example, epsilon closure Q0 can go to Q0, Q1, and Q2. If Q0 transitions from Q1 then to Q2, every epsilon NFA can be converted to a plain NFA by merging these closures into the transition function. Next, we have a simple epsilon transition animation, the free move. Finally, let us talk about the question. So the question here, basically, it is asking is how we can get a string that doesn't have 3 consecutive ones. So we can get it. So strings like 0, 1, 1, 0, 1, 1, 1, 0, 1 are accepted, but strings like 1, 1, 1, when we are getting 3 ones, or maybe 111 and 0, or maybe 111, 0, 1 are not accepted. So what is the core idea? So DFA needs to track how many consecutive ones it has seen so far. So basically, it can be done with the example. So the answer is B. So it can be done with 3 states. That is 0 once in a row, or maybe 1 once in a row, or maybe 2 once in a row. Whenever it gets 3 or more once in a row, it reaches a failed state. So basically, we have to get 3 state, 3 that is the accepted state, and 1 is the failed state. Next, my friend Raktik will continue. Thank you.
Good evening, sir. Am I audible?
Yes, please carry on.
Slide 14, equivalence theorem, NFA equals NFA and DFA. So now we arrive at the heart of Act 3, the big theoretical result that ties everything together. The Robin-Scott equivalence theorem, proved in 1959, tells us something surprisingly powerful. For every NFA that you can build, there is always an equivalent TFA that recognize the exact same language. In other words, NFAs don't actually give you any other expressive power over DFAs. They both recognize exactly the class of regular languages. Now, this does not mean NFAs and DFAs are identical. There is a cost. Converting an NFA with n state in the worst case, blow up to 2 to the power n states in the DFA. That's exponential. But in practice, the worst case rarely hits.
The constructive proof behind this theorem is subset construction, which is exactly what our next slide covers. Please move to the next slide. Subset construction algorithm. Subset construction is an actual algorithm we use to convert an NFA into DFA. The core idea is elegant. Each state in DFA represents a subset of NFA states, essentially a snapshot of every possible portion in the NFA could be simultaneously. Before we run the algorithm, we need to understand epsilon closure, which is the set of all states reachable from a given state using only epsilon's transitions without consuming any input. The algorithm itself runs in 6 steps. We start the DFA at the epsilon closure of the NFA start state, and for each DFA state and each input symbol, we compute where the NFA cloud could move to, take its epsilon closure and record that as a new DFA state, repeating until no new states appear. Except states in the DFA are in a subset that contains at least one NFA state. The maximum number of DFA states is 2 to the power n. But unreachable subsets are never generated, so the actual result is often much smaller. Please move to the next slide. Slide 16. Building the transition table. This slide walks through the subset construction by step on a concrete example. Our NFA has states like Q0, Q1, Q2 and alphabet of 0 and 1 and Q2 as the accept states. This animation fills the DFA transition table row by row. Each row corresponds to a DFA state, which is a subset of NFA states. As a new subset are discovered through transitions, they get added as new rows. Notice how the subset group together naturally. When we hit a subset containing Q2, the NFA's accept state, the DFA state gets highlighted as an accept state. This table is the bridge between NFA and the final DFA. Please move to the next slide. Once the transition table is complete, we can formally write down the full DFA. 3 things need to be pinned down. First, the start state. It is simply the epsilon closure of the NFA's original start state. It is our example. In our example, epsilon closure of Q0 is Q0 itself. Second, the accept state. Any DFA states that contain at least one NFA state qualifies. In our example, Q0, Q1 and Q2 is the only accept state since it is the only subset containing Q2. Third, dip or trap state. If any transition leads to an empty set phi, we add a non-accepting trap state that loops back to itself on all input, keeping the transition function total and complete. Putting it all together, our DFA has 3 states: Q0, Q0, Q1, and Q0, Q1, and Q2 with Q0 as the start and Q0, Q1, and Q2 as the only accept state. Please move to the next slide. Slide 18, the transformation. NFA morphs into DFA. And this final slide of Act 3 brings it all together visually. This animation shows the NFA on the left and the arrow in the middle and the equivalent DFA on the right, illustrating how subset construction transform into one into other. What is important to notice is that the structure changes. The DFA looks different, has different states, but the language it recognizes is identical. This is power of equivalence theorem. NFAs give us a convenient way to design and reason about machines. Subset construction gives us guaranteed path to a deterministic implementation every single time. Please next slide. Now we are moving to the gate question. This question asks us about the trace through a finite automata with 4 states: Q0, Q1, Q2 and Q3.
তোমার ওই স্ক্রিনটা সরাও, দেখা যাচ্ছে না তো। রাজিল প্লিজ ওটাকে সরাও আর ওই হোয়াটসঅ্যাপ বন্ধ করো কারণ সাউন্ড আসছে। ভালো প্রেজেন্টেশন হচ্ছে, ভেরি গুড। রাকেশ তো তোমার নাম?
ঠিক আছে, এখন দেখা যাচ্ছে?
হ্যাঁ, এখন দেখা যাচ্ছে।
Yes sir. This question asks us to trace through its finite automata with 4 states: Q0, Q1, Q2 and Q3 for the input string 0011. Thus, the machine starts at Q0 which has a self loop on both 0 and 1, meaning it states at Q0 when it reads a 0. Reading the first two characters 00 keeps us at the Q0 via that self loop. When we read the third character 1, the transition Q0 to Q1 fires, moving us to Q1. Finally, reading the fourth character 1 again triggers Q1 to Q2, landing us at Q2. Since Q2 is never reached during Q3 is never reached during the traversal, the complete set of states visited through the entire execution is Q0, Q1, and Q2, which is option A. Now, I would like to hand over the presentation to my teammate Sneha, who will explain the remaining topic, including DFA minimization and the final conclusion of our topic.
So in this slide, I'll explain the comparison of DFA and NFA. In DFA, for every state and input, there is exactly one next state, and in NFA, there can be multiple states including epsilon's transition. DFA follows a single path while NFA can explore multiple paths at the same time. DFA is faster with ON time and uses less memory. Since it tracks only one state, NFA tracks a set of states and can be slower. DFA may have up to 2 to the power n states, while NFA usually have smaller and easier regex to design. But both have same power. They recognize regular languages. So in practice, we design using NFA and convert it into DFA for execution. Please move to the next slide. This slide shows how DFA is used in lexical analysis. For the input int x equals to 1 equals to 5, the DFA left to right splits into token. Int is the keyword and x is the identifier and equal to is the operator. 5 is the number and each token is placed into its category. This process is also called tokenization and it is the first step in the compiler. Next, please move to the next slide. To summarize this slide, DFA is fast and used in real systems. NFA is easier to design and supports epsilon transition. Any NFA can be converted to DFA. These concepts are used in compilers, regex machine, and pattern matching. The key idea of Mealy machine theorem, regex, NFA, DFA are equivalent. They represent the same class of regular languages. Please move to the next slide. Here I will explain the gate question where let us first understand the NFA. There are three states. Q0 is the start state, Q1 is the accepting state, Q2 is the intermediate state. From Q0 on input A we go to Q1 which is accepting. From Q1 there is an epsilon transition to Q2 and from Q2 another epsilon transition back to Q0. This is also creating a loop. So what language does this accept? Starting from Q0, after reading 1A, we reach to Q1 and then accept it. Because of the epsilon loop, we can go back to Q0 and read another A. Repeating this process, so the NFA accepts one or more A's, which is A+. However, the empty string epsilon is not accepted because at the start of Q0 is not accepting. Now it is for the complement. Also, possible strings of A are A star, which includes epsilon. So the complement of all string is not A+. That leaves with only one string, that is epsilon. So the final answer to this question is complement of NFA is epsilon. Thank you, sir.
Thank you, sir.
Very good presentation. Thank you. Thank you. Next group,
Sir,
please.
could we group 6 start our presentation?
নিজেদের মধ্যে ঠিক করো, আমার কোনো আপত্তি নেই, আমি সবারটাই শুনবো, তাড়াহুড়ো করো।
স্যার, আই এম স্টার্টিং।
ঠিক, সব তোমার গ্রুপ মেম্বার সবাই আছে, ক্যামেরা রেডি আছে?
হ্যাঁ স্যার।
ওকে, স্টার্ট করো।
Sir, is the screen visible?
Visible.
Okay, sir. Sir, I'm Shorav Adhikari. I'm going to present today on the topic of Moore and Mealy machine. So before starting, we have to know about the finite state machine. What is the finite state machine? A finite state machine is a mathematical model of computation used in TOC and digital system design. It consists of finite number of state, input alphabet and output alphabet, and transition function. It has two main types known as Moore machine and Mealy machine. So what are the components of the FSM or finite state machine? It is first it is states, which is denoted by Q. That means finite state of states. Then it is sigma, which means input alphabet, which determines set of inputs, and then output alphabets, which is denoted by delta. It means set of outputs, and then there is a transition function, which is denoted by delta, and output function denoted by lambda, and initial state denoted by q naught. Next, we're going to start the Moore machine. What is Moore machine? A Moore machine is a FSM where output depends only on the current state. It has 6 components that are Q, sigma, delta, and del, lambda, and Q naught, which we discussed before it. Delta is a transition function which maps Q Cartesian with sigma, and lambda is the output function which maps Q to del. Moore machine characteristic out in here we can we can know the characteristics of Moore machine. Here output changes only when state changes. In Moore machine, output is associated with states. It is independent of input at that moment. It requires more states than Mealy machine. Output is stable, less noise. Here we will go through an example on the topic of Moore machine. Design a Moore machine to generate one's complement of a given binary number. So what would be the solution? According to first complement, if the given input is 1, then the output will be 0, and if the input is 0, then the output will be 1. For the first complement, there should be at least 3 states. One state is the start state, and the second state is the accept ones as input and produce output as 0, and the third state will be accept zeros as input and produce output as 1. Next slide will be continued by Surya Sahu, our next group member.
Yes, sir. I have discussed about Moore machine diagram. Is the diagram of Moore machine is just in the current state Q0 and Q1, Q1 and Q2. Is the diagram of Moore machine. One component Moore machine. I did not visualize the. There is a transition table, and the current is Q1 input value is 0. Then the next state of Q2 is output is 0. Then when Q0 is input value when
What happened, please?
Sorry, sir. My network is so slow. Sorry. My presentation when the current state Q1 is one input value is 0, when the next state of Q2 is output is 0. When the Q1 input value, when I record 1, then the Q1 next state of Q1 output value is 0. When Q2 input value I take 0, then the Q2 of next step is output value is 1. When Q2 understand Q2 input value I take 1, then the next state of Q1 output value is 1. So it's the next step. Where we discuss about advantage or disadvantage of more machine. Where the advantage is simple and easy to design it, and outside output stable, so no sudden charges, less sensitivity to input charges, and disadvantage are also requires more stages, slower response, output delay. So next slide. Now here we discuss about Mealy machine characteristics. Now the characteristics are also the output changes immediately with input. Now in a Mealy machine, the output is generated based on both the current state and the input. Because of this, any change in input produce an instant change in output without waiting for a state transition, and this makes the system faster and more responsive. Now, the next characteristic is requires favor states. My network is very slow, so I did not see the video slide. And the melee machines are more efficient because they often need fewer states to perform the same task as a more machine, since the output is handled during transition rather than states. The design becomes similar and more compact. Then the output associated with transition. Now in a melee machine, outputs are not written inside the states. Instead they are attached to transitions and other edges and represented in the form of input output or on arrows. This clearly show how the output is produced during state changes. And the next slide is explained by my friend Uday.
Good evening, sir. Today we are looking at Mealy machine, specifically Edge 11 sequence dictator. The key takeaway from this model is speed. Unlike the other state machine, in a Mealy machine reacts instantly. The output becomes one the moment the pattern is dictated, it without waiting for a clock trigger or a stage chance. This is because the output is directly function of the both current state and the current input, resulting in a highly efficient and fast reacting design. Second slide, please. The slide is Mealy machine diagram. Looking at the state diagram, we see the logic in the action. We start at from the S0. A0 keeps here. A1 moves us to S1, but the output is still 0, shown as 10. The magic happens at S1. If we receive another one, we trigger an immediate output of output of 1, shown as 11. If we get 0 at any point, the sequence breaks and we reset it to S0. It's a simple two-state solution of a pattern that would typically require from state in the other models. Second, next slide. This is state table. This table is mathematical backbone of our diagram. It maps a present state and input to determine the next step and the output by documenting every transition, like S0 receiving in A1 to transition output dictation, and we create the logic required to build the actual hardware. It's the bridge between the visual diagram and the physical circuit. Side seconds. Next slide. Advantage and disadvantage of Mealy machine. In the advantage are it efficient, fewer state means less hardware, lower cost and faster response time. It's perfect for complex system where the space is at a premium. And disadvantage, because the output react instant and output instantly to the input, it prompts the glitch of the noise. If your input signal is dirty, your output will be unstable. It's trade-off. You get maximum speed, but you must handle it expensivity. Next slide. Mealy machine to Moore machine convergence. Finally, if we need to stability, we convert the Mealy machine to a Moore machine. The process is straightforward. We identify the output of on the tradition and pull them into the state themselves. This usually increase the state count, but it synchronously the output with the clock by creating new state for each unique output and updating the transition. We trade a bit of speed and hardware which space for a much more stable glitch free system.
Okay, sir. So I am Onam today, and our topic is finite state machines. First of all, we in this topic we want to know that what is finite automata. So finite automata is a foundational concept of formal languages and automata theory. Finite automata define the simplest class of computation models, and from the theoretical backbone of compilers, pattern matching, and digital logging design. Abhishek, next slide, please. Yes. So first, in this topic, is an important part that what is finite state machine. So a finite state machine, or F is short form is FSM, is a mathematical model of computation that process and input a stream one symbol at a time, moving through a finite set of states and ultimately producing a binary design. So it's the main concept that ultimately producing a binary design, accept or reject. So here two part is sequential processing and finite states. Sequential processing is reading input symbols one at a time, left to right, with no ability to backtrack. Finite state is operates within a limited predefined set of states. And binary decision, that is after consuming the entire input, the machine either accepts or rejects the string. Next slide, please. Okay, so here are the some key characteristics of an FSM. Every finite state machine, regardless of its specific type, shares a core set of structural properties that define how it behaves and what it can compute. Finite number of states. The machine has a fixed countable set of states. This is what make it finite. It cannot grow its state space during execution. And second is sequential symbol processing. Input is read strictly left to right. Left to right. One symbol per stop. The machine cannot skip ahead or revisit previous symbols. Third is state transitions. Each input symbol triggers a transition from one state to another state, uh, governed by an transition function. Uh, and last is final decision. After the last symbol is consumed, the machine checks whether it resides in an accepting state of decide acceptance. Abhishek, next slide. Next slide is FSM as an abstract computational model. And FSM is not a physical device. It is an abstraction that captures the essence of computation under strict memory constraints, fixed memory. It reads an input step by step, updates its internal state according to fixed rules, and produce no output beyond the final accept or reject verdict. So the step is re-input. First of all, the read input consumes symbols sequentially from the input type. Second stage is change state. Apply the transition function, current state, and input symbol. And third stage is no external memory. The current state is the only memory the machine has processed. Next slide, please. Okay, so here the formal definition of a finite automation. A finite state machine is defined as five tuple. So first of all is a set of states. Second is input alphabet. Third is transition function, and fourth is initial state, and fifth is the state of final state. Next slide, please. Okay, so here the basic terminology. Before diving deeper into automata types, it's essential to internalize the vocabulary used throughout formal language theory. First, alphabet, a finite non-empty set of symbols from which input strings are formed. Second is string, a finite sequence of symbol, a finite set of symbol. Language, third is language. Language is a set of string that the automation accepts. Fourth is transition, the movement from one state to another triggered by reading an input symbol. Abhishek, next slide, please. Okay, so here the basic classification of finite state machines. As we can see that first FSMs are organized into two group families based on whether or not they produce output during computation. Each family contains specific machine types with distinct behavioral rules. First is FSM. Here in the FSM, we had two routes, without output and with output. In without output, we have DFA, NFA, and lambda NFA. And with output, with output, we have Mealy machine and Moore machine. Next slide, please. Okay, so here what is Mealy machine and what is Moore machine? In a Mealy machine, the output is associated with transitions. The output symbol is produced during the state change of depends on both the current state and the current input symbol. And in the Moore machine, the output is associated with states. The output symbol is produced when entering a state and depends only on the current state. Next slide, Abhishek. Okay, so here the deterministic finite automation, DFA. A DFA is the most valuable part and most predictable type of finite automation. For every state and every input symbol, there is exactly one defined next state. No guessing. So the state is exactly one transition and complete transition function, no epsilon transitions. Next slide, please. Okay. So here is non-deterministic finite automation, or NFA short form, and NFA relaxes strict rules of DFA. That is simply, if I can elaborate it simply, so allowing the machine to have multiple possible next state for a given input, despite the apparent freedom. NFS recognize exactly the same class of language as DFS. That is acceptance rule. And what is acceptance rule? The string is accepted by an NFA if at least one possible computation path ends in a final state. And next thing is NFA versus DFA. Every DFA is a fine trivially an NFA, but not vice versa. However, for every NFA, there exists an equivalent DFA. So, next slide is presented by my teammate Abhishek.
Yes, please carry on.
Okay, so moving on to the next slide, we have what is the difference between DFA versus NFA. So both models recognize the same class of languages, but they differ in how they process input. So let's talk about in very deeply. So in terms of DFA, what is the transitions? So in transitions, it has exactly one per symbol, but in NFA, we have 0, 1, or many. Now, if I talk about epsilon moves, in DFA it's not allowed, but in NFA it's allowed. Now, if I talk about state complexity, so in DFA may need more states, but in NFA, fewer states often suffice. Now, if we talk about computational power, so in DFA it is like same regular expressions, regular language, but in NFA we have also same regular language. Now, if I talk about implementations, in DFA we have deterministic, predictable, but in NFA we have non-deterministic and flexible. Now, moving on to the next slide, we have FSM, Finite State Machines. Its processing workflow. So a finite state machine processes input strings to a well-defined sequence of steps. So here is the exact workflow followed during string recognitions. So number one, we have start at initial states. The machine begins executions at the designated start state Q0 before reading any input. Then we have second step, that is read input symbol. The machine reads the next symbol for the input string, one symbol at a time, left to right. Then we have third step, which is move to next state. Using the transition function delta, the machine moves to the appropriate next state based on the current state and input symbol. Then we have fourth step. So it's repeat for all symbols, step 2 and step 3, repeat until every symbol in the input string has been consumed. Now, if I talk about fifth step, we have to check final state. If the machine ends in a state belonging to F, means accepting states, the string is acceptable, otherwise it is not acceptable. Then we have what are the three ways to represent an FSM. So finite state machines can be expressed in three complementary forms, each offering a different perspective on the same underlying mathematical objects. So number one, we have state diagram. So what is state diagram? It is a graphical representations where states are nodes, circles, and transitions are labeled directed edges. Accepting states are shown with double circles, intuitive and visual, ideal for understanding behavior at a glance. Then we have transition table, tabular format listing all states as rows and columns and input symbols as columns. Each cells contains the destination states, compact and precise, ideal for implementations and algorithmic processing. Then we have formal definitions, a five-tuple mathematical model like Q, sigma, delta, Q naught, F. This rigorous definition captures all components like states, alphabet, transitions, functions, start state, and accepting states in a single formal expressions. Now, if I talk about language acceptance example, so it's an even number of zeros. So we have to consider the language of all binary strings containing an even number of zeros. So this classic example illustrates how a minimal DFA tracks the simple parity property using just two states. So what are the two states? This is Q0, which counts zeros, accepting states, and Q1, which counts odd counts, zeros, not non-accepting states. So what are the things which is going to be accepted? So epsilon is going to be accepted, 0, 0 is going to be accepted because it is even, 0, 0, 0, 0 is going to be accepted, and 1, 0, 1, 0 is also going to be accepted. Now what are the things which are not going to be accepted, which are rejected? So 0 is going to be rejected, then we have triple 0, then we have 101, which is going to be rejected. Now how to convert this NFA to DFA? So we have subset construction method. So every NFA can be converted to an equivalent DFA using the subset constructions, means power state constructions algorithms. So this is a formal proof that NFA and DFA are equivalent in power. So what is the core idea of this? Each state in the resulting DFA represents a set of NFA states. The DFA simulates all possible NFA paths simultaneously by tracking which NFA states could be active after each input symbols. Then we have state exclusions. What is state exclusions? An DFA with n states may produce a DFA with up to 2 to the power n states, one for each possible subsets. In practice, many subsets are unreachable and can be ruined. Then we have guaranteed equivalence. The constructed DFA accepts exactly the same language as the original NFA. So this is a constructive proof that non-deterministic adds no expensive power for finite automata. Now talking about DFA minimizations, so it is a reducing to essential. After constructing a DFA, it may contain redundant states. So minimizations reduces the automata to its smallest equivalent form, unique up to isomorphisms. Now we have the partition algorithm. So what is this partitioning algorithm? So now the first step is initial partitions. So split states into two groups, accepting and non-accepting. These groups are distinguishable by definitions. Second, we have refined partitions. Two states are equivalent if they transition to the same partition on every input symbol. Split groups until no further refinement is possible. Then we have merge and output. Each final partition becomes a single state in the minimized DFA. The result is the unique minimal DFA for that language. So next we have minimizations in actions. Here we have an example. So this is a very good example. So let's walk through a concrete minimizations. Suppose we start with a 5-state DFA and apply the partitioning algorithm step by step. So what is the step? Step number 1 is initial partition. Separate accepting from non-accepting states. Then we have first refinement. Check transition within 2, 3, 4, 5. State 2 and 5 behave identically. State 3 and 4 behave identically but differently from 2, 5. Then we have final check. Step number 3, no further splits are possible. The partition is stable. All states within each group are indistinguishable. Then we have step number 4, which is the last step. It's a result to minimal DFA, 3 merged states. Moving on to the next slide, we have what are some of the finite state machine limitations. Okay, so over here we have not every languages can be recognized by a finite automata. So we have to consider the language L over here. Here in this question we have a string with an equal number of zeros and ones. So why FSM fails here? To accept this language, a machine must count zeros and ones and verify equality. For long strings, this requires unbound memory. The machines must remember an arbitrary large difference between counts. A finite automata has only finite states. By the pigeonhole principle, some two distinct counts must map to the same state, making them indistinguishable or contradictions. Now we have gate questions. So what this question is talking about? What is the complement of the language accepted by the NFA shown below? So we have to assume sigma equal to A and epsilon is the empty string. So over here option B is the correct one because the given alphabet sigma contains only one symbol A and the given NFA accepts all strings with any number of occurrence of A. In other words, The NFA accepts A plus. So therefore, complement of the language accepted by Automata is the empty string. Moving on to the next gate questions, we have a very good question, which is given the language L over here, which of the following strings are in L star, L complement? So over here, C is a correct option. Now, what is the explanation of this question? Any combinations of string in set A, B, A, B, A will be in L stars. So here we can see a very detailed explanation. Okay. So now I would like to conclude whatever I have talked about. So here, finite state machines are the foundation of automata theory. And what we have learned foundational concept. Then we have learned like DFA is equal to NFA in power. Then we have inherent limitations, and then we have real world modeling. So thank you.
Roy? Yeah.
Sir, is it visible?
Yes, visible. It is visible.
Okay, sir.
First slide is not visible, I think. Roy?
Wait.
Gate
Okay.
question is slide to that
Is it visible now?
Now it's okay. Yes.
Yeah. Okay, so the first slide is basically the compulsory slide, which is the group members page. The next slide would be the roll numbers and the details.
Okay. Carry on, please.
Okay, after this. The next slide, please. Okay, so the Church-Turing thesis is basically the thesis covers what the Turing process is, the machine, the Church-Turing thesis in general, and details about them. The next slide, please.
Just a second.
Okay, so the roadmap slide describes the contents that has been covered in this entire presentation. We have the historical context, what the Turing machine basically is, lambda calculus, the thesis that will describe what the basically the theory part of this entire thing. Then we have the equivalence, we have implications, which have examples, we have the physical CTT, and then modern relevance, which again brings up a few examples, and then we have a philosophical take, which is again complete theory basis. The next slide, please. Okay, so the historical context would be that in the 1900s, Gilbert's problem was solved. It's a mathematical problem that was fully formalized. In 1931, the incompleteness theorem was formulated, after which in 1936, both Turing and Church separately made their own papers. Church produced the lambda paper, which was based on calculus and the decision problem, and Turing gave the paper on computable number, which is basically a theory portion of this entire machine. Then there was this particular question that was very famous. It was given by Hilbert, which said that is there an algorithm that can determine whether any mathematical statement is provocable or not? This was solved by Turing and Church in 1937 with the equivalence. Next slide, please. Okay, so the Turing machine. Now, what the Turing machine is? The Turing machine is introduced by Alan Turing. It is basically a theoretical model that is used to understand how the computers work and perform computations. It works on the idea of reading an input and processing it, like step by step. Using like a set of rules and producing the output. So even though it's like a simple sort of abstract machine, it's very powerful and it's enough to represent any sort of algorithm that the real computers usually execute. So the basic components over here are given. One of the components is like the tape. Now the tape is basically, the tape is like a long strip. Now this strip is divided into different cells which are used as memory to store the symbols, like the binary digits, basically 0 and 1, or the symbol blank. There's this head which is basically the reader that reads the symbol and then it moves left or right and then reads the particular symbols 0, 1 and blank. The finite control, which is basically the set of rules that is predefined and decides what kind of action needs to be taken by the machine. So together it works and formulates the entire. The next slide, please. I think we have an example after this. Yeah.
So this example is how the Turing machine works. It's an incrementation of a binary number by 1. Okay. So it starts at Q0 and it moves right across the input. We have Q1, it reads the digit and then it sees that the digit is 1. So it changes it to 0 and continues moving right. Now this simulates the carry operation in binary addition. Okay. And then we have 0. Okay, it finds 0. Now this 0 is changes into 1 and then moves left after the completion of the addition. So finally when it reaches the blank symbol, it goes to Q3, which is basically the halt state. Now this halt state means that it stops and the function is complete. So overall it successfully runs the binary addition following step-by-step rules. That is the key word of Turing machine. So I'd like to call upon Shurju to take over the next portion of the presentation. Thank you.
Good morning, sir. I'm Surya Chaudhary, and I'm going to be continuing with the lambda calculus topic. Now, what is lambda calculus? It was given by Alan Turing. It was developed in 1932 as a formal system for expressing computation through function abstraction and application. It is a mathematical foundation of all functional programming languages. Now we look at the three important aspects. First is the variable abstraction. Now it takes a value x and returns the same value. Function application basically is the application of function with an argument x. And carrying in higher order, which is just the function returning another function. Looking at the Church numerals. Now we have four expressions here. Looking at the first one, we can see that if is being applied 0 times. That means it is just returning x. Secondly, we look at the expression and we can see that if is being applied only once. Subsequently, twice, and then at the last we have the successor function. Now, moving on to the key properties, we look at the alpha conversion. Renaming bound variables without changing meaning. X is being converted to y. Beta reduction. Substituting arguments for parameter. We have an example here. Moving on to eta conversion. Functions equivalent if same result. Now, an expression that we have here, it will return the function because x is not present as an argument in the f itself. Moving on to confluence. All reduction sequences lead to the same normal form. That means in the end we get the same result. Moving on to the next slide, we have the Church-Turing thesis. What it states is that every function that is naturally regarded as computable can be computed by a Turing machine. We have three equivalent formulations of computability. First one is the Turing machine, which was given by Alan Turing in 1936. A computational device with an infinite depth and finite control, the canonical model of computation. Looking at the lambda calculus, which was given by Church in 1936. A formal system for function abstraction and application, foundation of functional programming. Looking at the third one, that is the mu recursive functions given by Gödel, Herbrand, and Klein. Recursive definitions built from primitive operations equivalent in power to Turing machines. Moving on to the next slide, we have equivalence of computational models. Now what we look at here is that how all these three systems are interconnected with each other. Like the Turing machine is interconnected with lambda calculus by Church equivalence. Lambda calculus is connected with mu recursive function by Gödel-Herbrand representation, and Turing machine is connected to mu recursive by Klein encoding. What that means is that any function that is implemented through Turing machine can also be done the same by lambda calculus, and we can get the same result. Looking at the three aspects, we have simulation. Any Turing machine can simulate a lambda expression by encoding it as step symbols and state transitions. Encoding, any mu recursive function can be translated into a Turing machine via primitive recursion steps. And we have the expressibility. Lambda calculus can encode all mu recursive functions using Church numerals and recursion combinators. Now, the next slide, which is the halting problem, is going to be explained by my member, Surya Raut.
Am I audible, sir?
Yes, you're audible.
Yes, you're audible. So my topic is the halting problem. The problem, does there exist any algorithm
H that given any program P and input I correctly decides whether P halts on I or runs forever. So Turing's proof by contradictions in 1936. Step 1. Assume H function of P and I means program P and input I exists. If it's written yes, then P halts on. If P halts on, then return yes. If loops forever, then returns no. Construct a new machine D functions of P. If H functions yes, then D loops forever. If H function returns no, then D halts. Now ask, what does D function of D do? Means if D halts on D, it says yes, then D must loop. There is contradiction. If D loops on D, it says no, D must halt, and there has also contradiction. Both cases lead to contradiction, therefore H can't exist. The consequences is halting problem is undecidable. No Turing machine can solve it. Moving on to the next slide, please. Yeah. Next topic, undecidability and Rice's theorem. So there has famous undecidable problems, just like halting problems. Does program P halt on input I? Post correspondence, do two set of dominoes match? 10th Hilbert problem, integer solutions to Diophantine equations. Wang tiling, can a given set of tiles tile the plane? Kolmogorov complexity, is the shortest description of x less than equals to k? Virus detection, does the program contain malware? So the next topic, Rice's theorem. Any non-trivial semantic property of a program is undecidable. Formally, let P be a non-trivial property of partial function computable by a Turing machine. Then no algorithm can decide whether a program computes a function with property P. This means you can't write a program to check whether a program prints hello, whether a program ever outputs 42, whether two programs are equivalent, whether a program's output is sorted. Please move on, next slide. So there has computability hierarchy, the basic function, elementary function. There is content of simple arithmetic, addition, multiplication, exponential, etc. And it's included in primitive recursive functions, which contains for loop, bounded recursion, and alls, which is included in computable, better to say Turing computable functions. Turing computable functions may not terminate on all inputs. After that, the arithmetic functions, definable in piano arithmetic, not all computable. And at last, the all functions means all mathematical functions, uncountable, most can't not be named or described. Passing to the next slide, please. So this slide represents the physical charge Turing thesis. Every physical process can be simulated by a Turing machine. That means nature itself is no more powerful than a Turing machine. There are arguments for and arguments against. In the points of arguments for, first point, classical physics. Deterministic Newtonian mechanics is simulable by Turing machine with arbitrary precision. Second point, quantum mechanics. Quantum system can be efficiently stimulated on quantum Turing machines by Feynman in 1982. And the last, digital physics. Some physics, Wolfram Jews, argues the universe is a computation. There has arguments against. In this first point is analog computing. Real valued computation could in principle exceed Turing power, but physical noise limits this. Next point, quantum speed up. Quantum computers may solve problems exponentially faster, though not beyond Turing limits. And the last point in the arguments against, hypercomputation. Theoretical models, just like Oracle machines, Infinite Turing machines exceed Turing power but may not be physical. Moving on to the next slide. The next slide is quantum computing and the thesis, which is represented by my next member, Surya Roy.
Okay, next we have quantum computing and the thesis. What quantum computers can do? Number one, factor large integers exponentially faster. Shor's algorithm. Search unsorted databases with quadratic speedup. Grover's algorithm. Number three, simulate quantum systems efficiently. Feynman's original motivation. Number four, solve certain optimization problems faster. What quantum computers cannot do? Number one, solve the halting problem. Number two, decide any provably undecidable problem. Number three, compute non-Turing computable functions. Quantum Turing Machine. A quantum Turing machine (QTM) was formalized by Deutsch, 1985. It uses quantum superposition and entanglement. Key result: Bernstein and Vazirani, 1997. Any QTM can be simulated by a classical probabilistic TM with at most exponential overhead in time. This means quantum computers are computationally equivalent to Turing machines. They cannot decide anything a classical TM cannot, though they may do it faster. The quantum church Turing thesis. Any physically realizable computation can be efficiently simulated by a QTM. Moving on to the next slide, philosophical dimensions. Question 1. Is it a thesis or a theorem? Unlike mathematical theorems, the CTT cannot be formally proved. Effectively computable is an informal notion. Turing argued it is a definition, not a discoverable fact. Question 2. What is effective computation? This thesis says intuitive computability equals Turing computability, but intuition cannot be rigorously pinned down, making the thesis philosophically profound yet unprovable. Question 3. Could minds exceed Turing machines? Penrose in 1989 argued in The Emperor's New Mind that human consciousness may be non-computable. Most computer scientists disagree, but the question remains open. Question 4. Does Gödel's theorem challenge CTT? Gödel showed some truths are unprovable with a formal system. This limits what any algorithms can prove, but does not show humans can do more than Turing machines. Moving on to the next slide. A thesis, not a theorem. Mathematical theorem. Point number one, has a rigorous formal proof. Point number two, true in all mathematical models. Point number three, provable from axioms. Point number four, example, Pythagoras theorem. Similarly, in point number 5, we have an example, incompleteness theorem. Point number 6, cannot be refuted by intuition. Church-Turing thesis. Point number 1, informal mathematical conjecture. Point number 2, captures intuition about computability. Point number 3, cannot be formally proved. Point number 4, supported by evidence. All models agree. Point number 5, could be refuted by intuitions. Point number 6, a definition as much as a claim. Yet the thesis is universally accepted by computer scientists as the correct characterization of computability. Moving on to the next slide. We have modern relevance. Programming languages. Lambda calculus is the theoretical foundation of Haskell, Lisp, ML, and all functional languages. Every function as first-class object traces to Church's 1936 work. Cryptography and security. Rice's theorem guarantees no perfect virus scanner can exist. Proof-of-work systems are Turing computable. Computational complexity underlies all modern crypto. Distributed computing. Consensus algorithms, bitcoins, Paxos operate within Turing's limits. Smart contracts on blockchains are Turing complete, creating security implications. Artificial intelligence. Neural networks are Turing computable. AI cannot solve undecidable problems. Theoretical limits apply equally to all systems, no matter how powerful they seem. Computational biology, DNA computing and molecular computers are Turing equivalent. Gene regulatory networks have been shown to be computationally universal. Formal verification, proving program correctness is undecidable in general rise. Yet, bounded verification model checking is traceable as a direct consequence of CTT. Moving on to the next slide, the key takeaways are: number one, the Church-Turing thesis equates informal computability with formal Turing machine computability. Number two, Turing machines, lambda, calculus, and mu recursive functions are provably equivalent in computational power. Number three, the halting problem is undecidable. No general algorithm can decide if any arbitrary program terminates. Number four, Rice's theorem. No non-trivial semantic problem of programs are decidable. Number five, quantum computers are more efficient but not more powerful. They cannot solve undecidable problems. Number six, the thesis is a philosophical conjecture backed by massive evidence, not a provable mathematical theorem. Moving on to the next slide, we have gate questions. So the first question is, which of the following grammars are ambiguous? We have four grammars here given. So in first option A, in option A, the grammar generates strings like AA, BB, AAA, BBB, etc. Each string has only one way to be derived, so it is unambiguous. In option B, this grammar is ambiguous because operator precedence is not defined. For example, the string ID plus ID plus ID can be parsed in two different ways. Since one string has two parsed trees, the grammar is ambiguous. In option C, the grammar is also ambiguous. For example, the string A can be derived in two ways, using S produces AS produces A, or using S produces SA produces A. So we get two different parsed trees for the same string. In option D, this grammar generates strings like A, AA, AAA, and so on. Each string has only one way to be derived, so it is unambiguous. The next question, we have two DFAs, and we have to determine which of the following statements are true. We have four statements here, and the answer should be C and D, because both finite automates D1 and D2 accepts epsilon, and individually they accept some strings having length multiple of 3. L of D1 intersection of L of D2 equals epsilon. The string of length 3 accepted by D1 are 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1. The string of length 3 accepted by D2 are 0, 1, 1, 1, 0, 0, 1, 1, 0, and 1, 1, 1. That is, together D1 and D2 accepts all strings of length 3. Hence, the last option contains all strings of length divisible by 3. Moving on to the next slide. So I would like to end this PPT with the final quote of Roger Penrose, that is, the Church-Turing thesis is not just a technical result, it is a philosophical statement about the nature of mind and mathematics. Thank you, sir.